of STEAM education and is designed to promote problem solving, creative, and critical thinking skills, offer meaningful collaboration, and give hands on learning experience to the students. It is a much required step in the right direction for knowledge acquisition, empowerment, and honing the skills needed to make this world a better place to live in.
So, before we start, we have a short video for you, all in the memory of Dr. Ratnashri. So, now it is with sheer pleasure that I welcome a trailblazer with a clear vision, a eloquent communicator, a visionary with a laser like focus on the quality of instruction in the school, a dynamic leader who inspires teachers and students alike to achieve their potential. Such are the qualities of Ms. Anju Soni.
And a very good morning to all in one present here, and to some of us, a very good evening. The glorious Lamb of heaven, the Sun, has been the focus of the Educational Boot Camp 2021 for the last 1 month, full of engaging sessions in collaboration with IYNS, developing scientific understanding and observational skills of the students. We welcome and express our deepest gratitude to the facilitators for today. Dr. Akash Sinha from the Shiv Nadar University, Ms. Deepti Srivastava from Gurgaon campus, the mentors from Italy, France, who have been staying up late at night to provide this virtual tour to our students, our alumni, Uday Bhanu, Ekam and Jay from Shiv Nadar School, Gurgaon, Sonal, Siddhi and Siddhant from the Shiv Nadar University, who will be facilitating follow-up sessions in the end of December and January, along with Ms. Ripu Daman from the Faridabad campus. While we enjoy and engage with the sessions today, let's not forget there are a lot of exciting sessions on tomorrow. And let's look forward to the exciting panel discussion, which will have members not only from the scientific fraternity, but also the young learners. So over to you, Himanshi, and all the best for today.
Thank you, ma'am, for your insightful words. Now, we are inviting Mrs. Shiv Energy, ma'am, to say some words about our day 2 event. So, welcome, ma'am, in this educational boot camp.
Thank you so much. Just the energy of the morning, and that's what this entire celebration is all about. I was so mesmerized listening to you, Manshi, and your entire teammates. Thank you, Vinita, for giving us this opportunity on behalf of everyone present in this great space that you have co created. And lovely to see Uday, who's kind of just about walking through the portals. I don't even see the passage complete, except that you're already on another side of the time zone. But to all of you, and it was lovely to hear Anju with her words. All I want to say is that there is a whole interdisciplinary approach to looking at something as everyday and routine and as mesmerizing and magical as the sun. But as you said yesterday, and listening to Dr. Archana Sharma, Dr. Patrick Das Gupta yesterday, listening to Dr. Manjari, Rupa Manjari Ghosh, listening to all the students, one realized there is so much more in this exploration that keeps getting uncovered, even with a speck of speculation that everyone pulls in. So over to you, Vinita, and your team, because I can see they're waiting to take on. And thank you so much for this learning opportunity. All the best. Thank you.
Thank you so much, ma'am. When you start each day with a grateful heart, light illuminates from within. Some days you just have to create your own sunshine. So, what are we waiting for?
Today, the sunlight concealed the most brilliant of mosaics, reflecting from each leaf and wisp of cloud. It was as if there was a pure joy in the light, as if it were happy to create art where it shone warm and steady. It was as the smiles of friends, as fresh rain after summer sun, something to quench and soothe all at once. Aha, this is a very dear sun.
Think, is Earth the most important spot in the solar system? Think again. The sun is the real star of the show. Literally, the closest star to Earth. It's the source of all the heat and light that makes flowers bloom, songbirds croon, and sunbathers swoon. Life wouldn't exist without it. It's also the center of a solar system and by far its largest object. More than 1 million Earths would fit inside the Sun. Our star's enormous gravity grips the planet, dwarf planets, asteroids, comets, keeping them from spinning into deep space. Put simply, we wouldn't have a solar system without the Sun.
So, dear members, now it's time to get ready for session 1 of our day, Secret of the Solar System by Uday Bhanu Singh, alumnus of SNS who conducted EBC in the last edition and is with us today as an expert to share his knowledge, enthusiasm and passion. We welcome you, Uday.
Thank you so much. And thank you so much for that introduction. It's always a pleasure to be back here. I remember hosting EBC last year, and coming here again is just a genuine pleasure. So, as you also mentioned, today I'll be focusing on the solar system because I think the sun is the theme of your month-long event for EBC this year. And I think the solar system is about the most important topic related to the sun that one can discuss. And I feel that when we think about astrophysics, we think about a lot of topics that are exciting, like black holes and neutron stars and whatnot. But often it's really exciting to look relatively around us, although the solar system is huge. But sometimes it's just good to think about what's relatively closer to you and study that to see what could lie beyond and try to decipher the deeper mysteries of the universe. So I'll share my screen so that I can present a presentation. Should be loading up. Okay, well, let me try to present my screen in general. Can you see my screen? Can someone please confirm? All right, thank you. All right, so for the next few minutes, I'll be talking about the secrets of the solar system. So the solar system is a topic that we've been learning about since, I don't know, elementary school. It's one of the first things that you're ever taught, maybe in geography, maybe in physics. And it's something that's very close to us because we're a part of the solar system, right? We live on the Earth, which is a planet within the solar system. But it's really interesting to look at some details about the solar system that you often overlook. There's a lot that we know about it, but there's also a lot that we don't know about the solar system. And it's always a pleasure to actually look at what's around us in terms of the planets and in terms of their moons and in terms of their magnetic fields and the gravitational fields and so on, and try to figure out what's really happening here. So before I go on, I would like to mention some topics of interest that are areas of active research within the domain of the solar system. When we're looking at anything, any celestial body that's present in the solar system, there's a lot of stuff that we can look at, but 5 things that scientists are always looking for are its orbit, what's inside the planet or the moon, what's happening in terms of its internal processes, in terms of its volcanic process, what's immediately there on the surface. Do you see any craters? Do you see any mountains? Do you see any cracks? What can you immediately see on the outermost layer of the body? Then scientists always look at the composition of that celestial body. What is it actually made of? And where did that stuff come from? And there's also some stuff that is invisible to us visually, but plays a great role in shaping what the planet or the moon or whatever body that we're examining is really. These processes can include the magnetic field, their internal energies, and so on. So the reason why I mentioned these 5 things at the beginning is because whenever you're looking at any celestial body in the solar system, or now we're discovering exoplanets as well. So maybe when you're looking at exoplanets beyond the solar system, these are 5 things that you may want to look at, other than their names and other than their like placement in the solar system, which I'm sure you're already aware of. These are some things that can reveal greater details to you when you look at it from a scientific perspective. And I hope to show some of these to you and their implications on their planets, on other moons, and how we can think like astrophysicists, specifically as planetary physicists, to try to figure out what the solar system really is. So a basic review of the solar system before we go on. We all know that the solar system is called the solar system because the sun is present at the center of the solar system. That's where the word solar comes from. The sun is the primary source of gravitation. All the planets that are present in the solar system, all the asteroids, all the comets, they're all gravitationally bound to the sun. They're orbiting the sun. So the sun is sort of the heart of the solar system. Everything that we know, all the external energy that's provided to all these planets, all these bodies, comes from the sun. That's why it's called a solar planet, a solar system, as I mentioned. Then there are 8 planets: Mercury, Venus, Earth, Mars, Jupiter, Saturn, Uranus, and Neptune. There are 5 official dwarf planets. There may be a 6th one in the future. The most famous of the dwarf planets is Pluto. You've probably heard of it. Then there are asteroids present in the solar system. There's an asteroid belt between Mars and Jupiter. There are Trojan asteroids between Jupiter and Sun. And there are just general asteroids and meteoroids just spread out in the solar system, just rocky objects. Then there are also comets in the solar system, which are kind of like asteroids, but they have much larger objects, much larger orbits. And then, of course, there are meteors, which are just general rocks. Sometimes they land on Earth as well, which is how you get meteoroids. Very exciting. So that's what the solar system is made of: the sun, the planets, and all things in between. Now, the first thing that I want to discuss with you is differentiation. When we look at a planet, let's start from Earth, because the Earth is the planet that we know the most about, right? We've lived here for all of us ever since we started studying anything, really. So whenever we look at a planet, we look for a process known as differentiation. And differentiation really is a fancier word of saying layering. Each planet has layers, or at least we think that each planet has layers. This diagram on top right or top left for you is something that you must have seen since you were younger. It's a diagram of those different layers of the Earth. You can see a solid inner core, a liquid outer core, a mantle, and a crust. Now, why does differentiation really happen? Whenever there's a planet forming, you must have seen almost all planets are spheres, or at least they're spherical, which is because a planet is formed due to gravity, right? If there's a bunch of rocks, those rocks get attracted, they exert gravitational influence on each other, and in a large period of time, they form what is known as a planet. So there's gravitational contraction. Gravity takes all these rocks together, it compresses it until it becomes one solid object, right? So sometimes when there's a lot of gravity, some of that gravitational force becomes heat, because energy can take different forms, right? If it's like a mechanical force that's bringing these rocks together, sometimes that mechanical force can be so strong that it gets transformed into heat energy. And that heat energy can cause those rocks to melt, right? And when these rocks melt, they become liquid. And one thing about liquid is that it flows. So when the rocks that compose a planet becomes a liquid, it becomes fluid. And what happens when you pour oil in a cup of water? The oil floats to the top. Why? Because oil is less dense than water, right? Now you can see this at an astronomical scale happening with planets as well. When the rocks that a planet is made of gets melted, the less dense materials that a rock is made of sinks to the bottom, floats up, whereas the heavier material sinks to the bottom, right? And that's how differentiation occurs, with less dense material floating up and heavier material becoming the core of the planet. That's why you would see that if a planet is differentiated, its core would be solid at the center, because that's where everything is getting compressed. That's where all the heavier materials with higher melting points get sunk down to. Then you would see an outer core, which is usually liquid, which is because of, again, the gravitational contraction. And then you get the mantle, which is more and more solid as it goes up. And then there's a crust, which is more rocky material like basalt that forms the outermost layer. Now, what does this really imply? If a planet is differentiated like the Earth, it shows signs of internal activity, which means the planet, you can see activity occurring within the planet, which implies that the planet had enough mass to get differentiated. But again, because different planets have different masses, and because they're made up of different materials, some of them don't show differentiation at all, and they show differentiation in different ways. One very interesting example here in the middle bottom is the differentiation diagram of the moon. The moon isn't even a planet, it's a moon, right? I mean the Earth's moon. And here you would see an iron-rich core in the middle, which is shown in blue, with a yellow uneven asthenosphere, which is close to a mantle, but slightly more malleable, lithosphere, and a crust. So you can see that the moon is also differentiated, but it doesn't have as many layers as Earth does because it's not as massive as the Earth, right? It's much less massive. That's why it shows a lower degree of differentiation, because it never had enough energy to get differentiated to an equal extent. On the bottom left, you can see a comparison between the Earth and the Mars and the different layers. You can see that the Mars just has one core. The core is not differentiated into inner and outer, because again, the Mars isn't as massive as Earth. That's why it never showed any signs of extreme differentiation. And you can also see that the Mars has a much thicker crust, because a lot of the material that is present in the crust never melted. So it's just there. Now, things get interesting when you look at gas giants, because when you look at Jupiter and Saturn, you would see that they're mostly made up of hydrogen and helium, right? And these two materials, these two elements are already very light. They're the lightest things that we can possibly have when we're talking about elements. So you would see all of this hydrogen and helium floating upwards. So a large chunk of Jupiter and Saturn is just made up of gas. And it's only in the middle when you see a rocky core and some liquid ice. So this is very different from the Earth or Mars or even the Moon, where all of the planet's mass is either solid or liquid. Here in Jupiter, you see that about 80% of the volume is pure gas with a small rocky core in the middle, which is because the planet itself is made up of hydrogen and helium, which has no choice but to float up. The rocky core is stuck in the middle because there's no way for it to be distributed along the planet just because of how massive it is. Then in the ice giants, which are, you would see a similar composition to Jupiter and Saturn, but because they're less massive, the gas volume is slightly less in terms of its ratio with respect to the planet. You would see a larger rocky core, as you can see in the diagram at the middle. Again, Jupiter and Saturn, like Jupiter and Saturn, Neptune and Uranus are also largely made up of liquid hydrogen and helium, but in this case, there's less gaseous hydrogen and helium because these planets are less massive. So sometimes liquid hydrogen and helium and form ice, which is why they're also called the ice giants. So this differentiation process really tells us that the amount of energy is directly dependent on the amount of mass that a planet has, and this can lead to a differentiation in a planet that tells us how that planet is layered. So if you start going deeper into a planet, we know what we'll find because we can study this differentiation process. And I've always found this very interesting. Another thing that you find when you look inside the planet is volcanism. By volcanism, I mean stuff that is inside a planet shooting up. Simply put, volcanoes are very common on Earth. You might have seen one, you might have not. They're not common in India, at least on the main surface. But as you can see on the large diagram on the left, when a lot of heated material in the inside and the internal parts of Earth gets heated up, they often shoot out of the crust, and this shooting out of the crust forms what is known as a volcano, which basically acts as a duct that allows materials from the mantle to come out of the crust, right? So, what does volcanism really tell you about a planet? It tells you that there's a circulation happening, right? Again, finding volcanoes anywhere in the solar system is a sign that that planet is, again, alive in a way. There's activity happening there. There is energy being transferred into different forms. There's something happening that is making material shift states and shift positions. So, in a sense, that the world is alive. Volcanoes have been found in a lot of the worlds, but the thing is, volcanoes aren't always active. On Earth, we see that most of the volcanoes that we see now are not active. They're dead volcanoes, but we still have active volcanoes. That means that the Earth is still alive in a way. If you look at Venus, you would also see some volcanoes that are alive, which is because of the giant mass of Venus compressing materials towards the core, and the cores and the mantle material shooting up, just like the Earth. But an interesting example in the solar system is that of the moon Io. Io is spelled literally just I and an O. It's a moon of Jupiter. It's the fourth largest moon of Jupiter. And it's one of the first worlds that we discovered outside of Earth and Venus that was shown to have active volcanoes. But something is very special about the volcanoes that are present on Io, because unlike Earth volcanoes, which usually shoot up silicates, Io's volcanoes usually shoot up sulfur and sulfur dioxide. So most of the discharge that is present on Io is made up of sulfur. But there's something more interesting about the volcanoes on Io, which is that the volcanoes aren't actually caused by gravitational contraction. They aren't actually caused by internal energy, but they're actually caused by what is known as tidal distortions. So what this word really means is that when Io is orbiting Jupiter, um, it a certain amount of gravitational force gets exerted on Io's both sides, right? So when you have a ball that is somewhat liquid getting pulled and pushed by another object, it contracts, then it expands, it contracts, and then it expands, and it gets a lot of energy, right? That happens to every single moon. But in the case of Io, it's not just Jupiter that's exerting this energy. Jupiter also has moons such as Ganymede and Callisto, which are, again, very large moons, which also have gravitational influence over Io. So Io is getting pulled in all these different directions. It's also getting pulled by Jupiter. It's also getting pulled by Ganymede. And because of this, and when it gets very frustrated, it wants to cry in a way. And that's what volcanoes are. It's because of all this activity that's happening in Io internally because of external pressures, which is why these volcanoes burst out, which is unlike any other world that we've seen. On Earth, volcanoes only occur because of internal activity. On Io, it's all external. Another thing about volcanoes is that they can tell you how recent the surface of that planet is. For example, when you look at the moon just outside your window tonight, you would see certain areas of the moon that are completely plain, right? They're called Maria. They're these black regions that have no craters. Now, one thing you should know about the solar system is that when the solar system was being created, there were asteroids and meteors everywhere. So every single planet, every single moon should have craters on their surface pretty much everywhere. But what happens to these surfaces is that whenever there's tectonic activity or whenever there's volcanic activity, these craters get dissolved, craters get dissolved. That's why you don't see a lot of craters on Earth, right? If you just take a drive, you're not likely to come across a crater because Earth has earthquakes, Earth has tectonic activities, Earth has mountain formation, which is why these craters get dissolved. Similarly, if you see large, smooth plains on any surface, on any planet or moon in the solar system, it's a sign that there were volcanoes there, at least at some point. Maybe they're inactive now, but it shows a sign that there was volcanic activity on that world at some point in history, which also tells you that that planet was alive at some point in history, which can tell you a lot about the history of the planet itself. Then we can look at craters. What do craters tell us? When you're looking at craters, you can see the history of crater formation. On the diagram to the right, you can see how craters are formed. There's a projectile that hits a surface. When it hits the surface, it's traveling so fast it causes an explosion, right? And when it causes an explosion, it causes shock waves to travel below to the surface, and it also causes material that was previously present on that surface to spread out. And it also causes the projectile itself to be broken apart and then be distributed across the planet, which is why a sort of dome shape is a reverse inverse dome is formed whenever something hits a surface, which is the crater itself. Now, that inverse dome also gets filled up by the surface, by the material that was produced during the explosion, which is why when you look at a crater, you would usually not see a complete dome. You would see something like this that you can see in the diagram. It's almost like a flat, it's almost like a deep plate where the bottom is usually flat because even though it would have formed a dome, the dome itself gets filled up by the explosion, by what's produced in the explosion, which is why craters have this distinct shape. And there are all the ejection flows in different directions, which causes separate secondary craters to be formed everywhere. And that is how craters are formed. And a general rule of thumb in planetary astrophysics is that more the craters, older the region. If you look at a particular spot on the surface of any world and it has a lot of craters, you can say that that world is very old. And similarly, if you compare photos from one region of the planet to another region of the planet, and one region has more craters, you can almost definitely say that that particular region is older than the region with less craters, because craters are an indication of how old that region is, which is a great tool for astrophysics because all you have to do to figure out how old a place is to look and count the number of craters, which isn't very difficult. Um, yeah. So, what else can you see on the surface of a world? You can see cracks in mountains. On the top left here, there's a photo of Valles Marineris, which is the largest canyon in the solar system, which is present on Mars. So what happens in a world is that when the world is being formed, and by a world I mean either a planet or a moon, when it's getting formed, it goes through a series of compressions and expansions, right? As I said, when gravity is pulling all the material together, it's releasing some heat energy, which is causing some materials to expand or contract, right? Just like iron. If you heat up iron, it expands, right? Just like that, when there are silicate rocks, they go through series of compressions and contractions and then expansions. And when this is happening, they give rise to cracks and ridges. It's similar to when you're baking a cake, right? When you put in a batter inside an oven, you would often see that the surface of the cake that comes out of the oven is smooth, but oftentimes you would see one crack on the cake's upper layer, right? That's because certain energy from the bottom gets pushed upwards, which causes a crack in the surface. So you can consider these planets as giant cakes being baked in the solar system. Sometimes they develop cracks, and these cracks are, again, an indication of what's happening inside, how much energy is there. Below, you can see an image of what's known as lenticulae on Europa, which is, again, a moon of Jupiter. And what lenticulae are these lines or these updwellings of air that come through Europa's liquid surface. So they're in a way an indication of the energy being um, vaporized from the core of Europa to the surface, and they take a slightly different form because a large chunk of Europa is just liquid, and liquid behaves different from the rocky surfaces of Mars. So on Mars, you see one giant canyon, whereas on Europa, you see lenticulae, which are like tiny canyons, but just vastly spread out. On the right here, you can see an example of Venus, which behaves in a similar way to Earth, but sometimes these convection currents just pile up and form these updwellings that give rise to what are known as scarps on the surface of Venus. So they behave in very similar ways, but the variances are dependent on the amount of energy that is present inside these surfaces, inside the planet. Then I'd briefly talk about the composition. When you look at terrestrial planets, which are Mercury, Venus, Earth, and Mars, you would see that they have a higher density and they're made up of rocks. When you look at Jovian planets, you see a more varied density, with Jupiter's core being as dense as 31 grams per centimeter cube, which is much, much larger than the density of the Earth. But the average density of the planet, because it's mainly gas, mainly hydrogen and helium, is just 1.3 grams per centimeter cube, which shows how diverse the regions of the planet really are. Um, a very interesting occurrence in the solar system is the difference in internal energy between Jupiter and Saturn. You would see that even though Saturn is much smaller than Jupiter, it has an internal energy that is only slightly smaller than Jupiter. Specifically, you would see that Saturn should have much less primordial heat because it's only 1/4 as massive as Jupiter, but its internal energy is actually just half of Jupiter. So there must be something else happening inside of Saturn that's giving it more internal energy, right? And this internal energy, through scientific theorization, comes from helium and hydrogen getting differentiated. Again, as I said, helium is slightly more heavy than hydrogen, right? So whenever there is hydrogen and helium present in the interior of Saturn, the helium sinks down and the hydrogen like floats up. And this separation releases extra energy in Saturn that does not happen in Jupiter because Jupiter is too massive, it compresses everything, which is why Saturn has extra internal energy, which is really fascinating because it shouldn't, but this simple process of hydrogen and helium getting separated physically can cause Saturn to have much more internal energy than Jupiter. And as I mentioned, another source of internal energy can actually come externally from tidal distortions, like I discussed in the case of Io. Now, one more topic that's very interesting in terms of planetary astrophysics is magnetic fields. Um, we know that the Earth has a magnetic field because if it didn't, we would probably not exist. The magnetic field protects us from what's known as the solar wind, just particles from the sun rapidly flowing everywhere in the solar system in all directions. So, what actually causes planets to have magnetic fields? It's very similar to a dynamo, which is an engineering device that you've probably seen. When a planet has a lot of liquid iron that can flow inside the planet's core and it rotates, this rotating conductive fluid causes the planet itself to develop a magnetic field, right? It's very similar to stuff that you would have studied in your electromagnetism classes, where a planet itself, instead of it just being a small device, the planet itself becomes a huge magnet because magnetic fluid in the core flows very fast and develops a magnetic field. And this is known as the dynamo theory, which is how planets like Mercury and Earth develop magnetic fields. It's slightly different in Jovian planets because Jovian planets do not actually have molten iron, right? As I discussed, Jupiter, Saturn, Uranus, and Neptune, they're mostly made up of hydrogen and helium, which begs the question, how do they have magnetic fields? And something very interesting about these planets is that they're made up of hydrogen, and hydrogen, when it's compressed to very low temperatures, uh, to the point when hydrogen itself becomes a liquid, starts behaving like a metal. And when this hydrogen starts behaving like a metal, it acquires the same role that the iron does on Earth, and which is why metallic liquid hydrogen acts like a conductive fluid for that planet. And one thing that's true about all Jovian planets is that they rotate very fast, which is why these planets develop huge magnetic fields. In fact, Jupiter's magnetic field is so big, you can see in the diagram, that it actually extends to Saturn's orbit. So there are points in Saturn's orbit where it actually crosses through Jupiter's magnetic field, because Jupiter's magnetic field is 20 to 30 times stronger than that of Earth. It's just insanely big. And that's how these planets also have magnetic fields much stronger than the Earth. In the case of Uranus and Neptune, we don't actually have metallic liquid hydrogen, but we have something known as hydrogen water mantle, which is still an active area of research. We're not sure about how these planets have magnetic fields. I'm almost out of time, so the last topic that I'll discuss briefly is the Kuiper Belt and the Oort cloud. These are the last regions of the solar system which we basically know nothing about. The Kuiper Belt is a torus or a donut shaped region that is outside Neptune. It's about 30 AU, and 1 AU is the distance between the Sun and the Earth, which is 150 million kilometers. So the Kuiper Belt is about 30 AU away from the Sun, and it contains a lot of objects that are known as Kuiper Belt objects or trans-Neptunian objects, which are usually icy and rocky objects that are spread across this donut-shaped region. A very important example of an object present in the Kuiper Belt is Pluto, which used to be a moon, but we realized that it doesn't meet all the requirements. So the Kuiper Belt contains all these icy worlds that are yet to be discovered. Probably no planets. They're usually icy and moons or icy asteroids that are present in this large region, but it's still an active area of research. The last region in the solar system is the Oort cloud. And the Oort cloud is literally the edge of the solar system, but calling it an edge is a bit of a misnomer because it extends from about 2000 AU to about 100,000 AU. And 100,000 AU is about 1.5 light years. And the nearest sun and the nearest star from Earth, except the sun, after the sun, is about 4 light years away. So the Oort cloud actually extends more than a quarter the way between the sun and the nearest star after the sun from Earth. So that's how massive the Oort cloud is. And the reason why this exists is because the sun is so massive that it can cause gravitational influence to these lighter, smaller objects to this distance as well. It's the spherical region which encapsulates this entire radius that I talked about, and it's made up of icy comet-like objects. So these are objects with very large orbits that rotate around the sun. We will likely never see them in our lifetimes, and they're just hugely spread out in the solar system. And that's what the solar system is. It's the edge of the solar system. Anything beyond that is beyond the gravitational influence of the sun. The sun has no control over anything in the universe outside of the Oort cloud. So that's where the solar system ends, and it really shows how much we don't know about the universe. There's a lot of stuff that we have figured out, but there's a lot of stuff within this domain that I talked about that we don't know about. So that
So, thank you, Uday, for such a stimulating and informative session. And you know, our audience is full of thoughts and doubts now. We have some questions coming from audience. So I request you to answer them. So here is the first question we have. How will learning about other planets help us in a life on Earth?
That's a great question. Um, Learning about other planets really tells you about processes that are relevant to the Earth as well. For example, when we're looking at Io, moon of Jupiter that I discussed, you see that the volcanic activity can be caused by factors that are not even present within the planet itself. And that tells us how we can study certain phenomena on Earth that we may not have looked at from perspectives that are not directly present on Earth. For example, if we discover a volcano that we cannot explain by internal activity, we would not have known that it can be caused by tidal distortions in the past. But because we've looked at these tidal distortions happening on Io, we can consider that possibility and actually try to figure out what's happening on our planet. And other than that, studying other planets tells us that, oh, okay, if we ruin the Earth, which we shouldn't, by the way, but if we do, what are the other worlds that we can consider to give us life and to sustain life, which is, again, an active area of research.
Thank you, Uday. Now the next question is from Himaksh Manchanda from Standard 6 Shiv Nadar School. The Earth's surface is dry and wet but has a very hot crust. In Neptune, it's all blue, but is the crust blue too? Wouldn't it be a different color? What adapts it a blue color?
Right, that's a great question. So, what gives Neptune and Uranus as well that blue color is the presence of methane. So, what happens is that when you're looking at a planet, you're looking at a lot of things happening together. When you're looking at the Earth, um, the reason why a lot of the surface of the Earth appears to be blue, green, is because you're directly looking at either water or land or trees, something like that. But when you're looking at Neptune or Uranus, you're looking at a mixture of hydrogen, helium, methane, ammonia, and some other gases. And it's the presence of these constituent gases, like methane and ammonia, which give them the bluish color that we can see. So, again, the Uranus doesn't really have a crust. Most of the surface that you see from your perspective is just gas. And it's because of this mixture of gases that it acquires a blue color because methane is the primary gas that is present in these planets.
Okay, so another one we have that what do you think is there is a chance to have a Big Bang again?
Chance of having a Big Bang again. The thing is, we don't even know if the first Big Bang happened in the first place because the Big Bang is a theory, right? So
Yes.
if we assume that the Big Bang happened, first we need to figure out why did it happen in the first place before we can think about whether it can happen again. So that's a very intriguing question, but it's so broad that we don't really know anything about the Big Bang in the first place to actually think about whether there can be another Big Bang. So I'm going to leave that for theoretical physicists at Caltech or MIT to figure out.
Thank you, Uday. So we have another one from Himaksh. It's uh, do asteroids exist? Because Kuiper belt is filled with asteroids with some harmful gases, but never heard of crashing on any planets.
Okay, so the thing with asteroids is that asteroids are always in an orbit, right? Nothing in the solar system exists just independently. All the objects orbit around the sun in certain ways. So the reason why you don't see a lot of collisions with planets these days is because the solar system has existed for so long that it has reached some sort of a stability. If you looked at the solar system about, I guess, 5 billion years ago, you would see collisions everywhere. And now, because all these asteroids are in stable orbits, you would see less collisions. But yes, asteroids are present everywhere in the solar system, but they're concentrated in certain regions, such as the asteroid belt, the Trojan areas, which are the Lagrange points between Jupiter and Saturn. So the asteroids are usually concentrated, clumped together in certain regions, which is why you don't see a lot of collisions, but they're spread out in the Kuiper belt, in the asteroid belt, near the Earth, near Mars, etc. They're everywhere.
Thank you, Uday, for such informative answers. Hope so our audience are satisfied now and we learned a lot from you. Thank you so much.
Thank you so much. It was a pleasure being here, and I hope others enjoyed as well. Thank you so much.
Can I just pitch in here?
Yes, ma'am.
So, Uday, I was so amazed to see that all questions which were asked are sixth grader students, and there are many more questions. We will take all these questions, copy paste, and share by mail, so that, and when you answer it, I'll share among all schools those who are watching. So, thanks for igniting young minds, and especially the grade six by your, you know, the most one of the most loving thing is that when senior educates junior, and you, though you have joined college and you are not, you're my ex student, but I don't accept it. You will never be my ex. You had written a card while going, till be alive, I'll be there whenever you call me. And thanks for always being with us, Uday. Love you a lot.
Yeah, it feels very good to be back here, and I hope that I see someone else researching about planets in the future and try to look at this area of astrophysics. Okay.
So, audience, this is very important to share. He is pursuing astrophysics in Georgia Tech, USA, and he was very excited. He was my student, and he will be called again, obviously. And because there are so many questions there from Gurgaon sixth graders. I mean, if I allow you, you can stay here for another 1 and 2 hours. So we will call you especially for our sixth graders because they are not watching you today and they are missing your session.
I'll be here for sure. That'll be fun. Yeah.
Thank you.
Thank you so much, and good luck for the rest of the day.
Shashi ma'am, would you like to speak? Would you like to speak? You are on mute.
No words, Uday.
Thank you. Thank you so much,
You're
ma'am.
there amongst the stars, so just be there.
And Shashi ma'am, this is important to mention. This idea was given by Matthew. When I was in panic that, so he said, you have so many ex-students, connect with them and call them. So if this name came first in my mind.
Absolutely. Matthew, a big thank you. And Uday, all the best. Be there for us always. Thank you. Yeah.
Matthew, we have session of Dr. Deepti Srivastav and grade 9 students from Gurgaon. Again, this is a student-led session. Would you like to add one or two lines for Dr. Deepti Srivastav from Gurgaon and 9th graders Gurgaon student? Over to you, Matthew.
Well, I'm speechless only because our students always amaze me. And that's how it should be. And it excites me because the paradigm we have at Shiv Nadar, it is student-centred. And these sorts of sessions just show what our school has become and is growing to be, because our students lead our learning. And I know they'll take sessions like this, be it older students with younger students or younger students just working with their own grade. So what excites me is that we are now shaping the school that we talk about. It's not just words, they're actions. And Benita and your team, thank you so much, because that reality is not easy to achieve. And as I said, I think we're leading the way and exciting times ahead. So congratulations to you, your team, our students. It's a wonderful environment to be part of. So keep it going. Thank you.
Thanks.
Thank you so much, sir, for your motivating words. And now, Soumya, do you know a word is striking to my mind with the letter C? And it also has a rhythm in it. Aha, wait, I will tell you. It's none other than circadian rhythm.
Oh, great! What's that? And what next in the line to go?
Okay, so you have to wait for that. Hold your heart back and have patience. Today we have Ms. Deepti Srivastava, an avid bioeducator for Shiv Nadar School, Gurgaon, along with a student from grade 9th, who will be conducting an interesting session related to circadian rhythm. Let's welcome her into a world of learning and science.
Thank you so much for the kind words and the introduction. I'll hand over the presentation to Dia, who is going to introduce the team because we've been working on this very interesting topic for the past few days. So over to you, Dia.
Getting up in the morning? And do you sleep later during the school holidays? There is actually a biological reason for people to wake later, and it's all based around your body clock, or more precisely, your circadian rhythms. The rotations of the earth around the sun and the moon around the earth produce the cycles that we know as night and day. Animals and plants have rhythms that match these cycles too. A simple example of this activity is linked to day and night. Daily rhythms such as these are called circadian rhythms. Today, our group, which includes me, Diya Dadu, Jay Mahanta, Ekam Singh, and Devasya Sharma from 9 Corbett Shiv Nadar School, Gurgaon, is going to share a small presentation about this fascinating and important phenomenon. Let's now watch a small video to understand this phenomenon better.
In 1962, a cave explorer named Michel Cerf started a series of experiments where he isolated himself underground for months without light or clocks. He attached himself to electrodes that monitored his vital signs and kept track of when he slept and ate. When Cerf finally emerged, the results of his pioneering experiments revealed that his body had kept to a regular sleeping-waking cycle. Despite having no external cues, he fell asleep, woke up, and ate at fixed intervals. This became known as a circadian rhythm, from the Latin for about a day. Scientists later found these rhythms affect our hormone secretion, how our bodies process food, and even the effects of drugs on our bodies. The field of sciences studying these changes is called chronobiology. Being able to sense time helps us do everything from waking and sleeping to knowing precisely when to catch a ball that's hurtling towards us. We owe all these abilities to an interconnected system of timekeepers in our brains. It contains the equivalent of a stopwatch telling us how many seconds elapse, a clock counting the hours of the day, and a calendar notifying us of the seasons. Each one is located in a different brain region. Cerf, stuck in his dark cave, relied on the most primitive clock in the suprachiasmatic nucleus, or SCN, of the hypothalamus. Here's the basics of how we think it works, based on fruit fly and mouse studies. Proteins known as CLK, or clock, accumulate in the SCN throughout the day. In addition to activating genes that tell us to stay awake, they make another protein called PER. When enough PER accumulates, it deactivates the gene that makes clock, eventually making us fall asleep. Then, clock falls low, so PER concentrations also drop again, allowing clock to rise, starting the cycle over. There are other proteins involved, but our day and night cycle may be driven in part by this seesaw effect between clock by day and purr by night. For more precision, our SCNs also rely on external cues like light, food, noise, and temperature. We call these Zeitgebers, German for givers of time. Seif lacked many of these cues underground, but in normal life, they fine-tune our daily behavior. For instance, as natural morning light filters into our eyes, it helps wake us up. Traveling through the optic nerve to the SCN, it communicates what's happening in the outside world. The hypothalamus then halts the production of melatonin, a hormone that triggers sleep. At the same time, it increases the production of vasopressin and noradrenaline throughout the brain, which help control our sleep cycles. At about 10 a.m., the body's rising temperature drives up our energy and alertness, and later in the afternoon, it also improves our muscle activity and coordination. Bright screens at night can confuse these signals, which is why binging on TV before bed makes it harder to sleep. But sometimes we need to be even more precise when telling the time, which is where the brain's internal stopwatch chimes in. One theory for how this works involves the fact that communication between the same amount of time. So neurons in our cortex and other brain areas may communicate in scheduled, predictable loops that the cortex uses to judge, with precision, how much time has passed. That creates our perception of time. In his cave, Seif made a fascinating additional discovery about this. Every day he challenged himself to count up to 120 at the rate of 1 digit per second. Over time, instead of taking 2 minutes, it began taking him as long as 5. Life in the lonely, dark cave had warped Seif's own perception of time, despite his brain's best efforts to keep him on track. This makes us wonder, what else influences our sense of time? And if time isn't objective, what does that mean? Could each of us be experiencing it differently? Only time will tell.
Thalamus and synced to solar day and night. It predicts and prepares for our daily activities, coordinating the bodily functions that accompany those activities from the time we wake up through our sleep. Circadian rhythm refers to the physical, mental, and behavioral changes that occur in most living things over a 24-hour cycle, primarily regulated by the light, darkness of the surroundings. We've learned that while there is a master clock in the brain, almost every cell in the body has its own biological clock. Each cell keeps time through the expression of certain genes and proteins, becoming active at certain times through a 24-hour period. The explanation of that mechanism earned a Nobel Prize in 2017, and since then, other researchers have gone on to find these clocks everywhere across the body. In the natural world, sunlight is the strongest time cue for these clocks. It sets the timing of the master clock, which then coordinates the processes that occur throughout the body, including the early morning processes that promote wakefulness, as well as when we eat, when we are active, and the processes that control sleep. Before the invention of artificial light, circadian rhythms were determined by the rising and setting of the sun. People got up around sunrise and they went to bed shortly after sunrise, even as the seasons changed. Artificial light, however, has changed that equation. Because electric light allows people to conduct daytime activities after dark, many people's circadian rhythms and sleep schedules have been thrown off. Long work days, night shifts, eating late at night, and even just staying up to binge watch favorite TV shows into the wee hours disrupt the natural sleep wake cycle once determined by the sun. As a result, many people in modern society suffer from poor sleep. Misaligned circadian rhythms and lack of sleep have been linked to depression, cognitive impairment, obesity, heart disease, diabetes, and mood disorders.
Now, look at these two images. What two birds do you see? Most of us know these birds as the owl and the lark. Now you'll be wondering, why are we talking about these two birds? Well, us humans behave like these birds. I'm not saying we eat worms or fly like them. I'm saying a circadian rhythm makes us behave like these birds. Let me show you how.
Let's now conduct a personality test to test whether you are a lark or an owl. I'm putting the link in the chat and please complete the questionnaire in the next 5 minutes.
I hope everybody has done the quiz. Now, now that you know that if you're a morning person or a night person, let me show you how owls and larks are connected to this. Some humans are called larks because larks start the day very early. This explains the choice of the word lark. These people sleep from around 10 p.m. to 6 a.m. or even earlier. Human larks tend to feel more energetic just after they wake up in the morning. They are thus well suited for doing the most complex tasks in the morning. On the other hand, we have the human owl. These people are the exact opposite. They wake up late at night. This explains the choice of word for owl. These type of people stay late at night or even early hours in the morning. They can do the most complex tasks at night. Now I'll be showing you a video which will explain this phenomena even more.
You may have heard the saying, the early bird gets the worm, but when it comes to humans, do morning people really have an advantage over night owls? Does one come out on top as more intelligent or successful than the other in this battle over bedtime? The somewhat surprising truth is that we have little say in sleep preference, as it's almost entirely genetically predetermined. Chances are, if you're a night owl, it was likely passed down from an ancestor who was also a night owl, and from an evolutionary perspective, it makes sense. Having individuals with varying sleeping patterns would allow for better protection of a group throughout the day and night. Instead of everybody sleeping at one time, some people naturally stay up later and some wake up earlier, aware of threats or predators, while others sleep. But considering most modern societal activities happen between 9 a.m. and 5 p.m., it may seem clear that night owls are put at a disadvantage. And researchers have actually coined the term social jet lag to describe the sleep deprivation many experience to accommodate social norms. For night owls, this social jet lag feels like living in a different time zone every single day. Considering chronic sleep deprivation has a direct effect on brain functioning, it's no surprise that studies report night owl university students have lower overall grades. Not to mention, early birds tend to display more positive social traits, such as being proactive and optimistic, and are less prone to depression or addictions to nicotine, alcohol, and food. And we can see these traits represented physically in the brain, particularly the white matter, which helps neurons communicate. Night owls exhibit significantly less white matter, and as a result, there are fewer pathways for feel-good hormones such as serotonin or dopamine to travel through. But it's not all bad for the late-nighters. In fact, they tend to be much more creative, have been found to have higher cognitive abilities, and are known to be risk-takers. What they lack in white matter, they make up in cortisol levels. This stress hormone gets your body ready to face an immediate threat, contributing to their risk-taking behavior, which studies show can translate into opportunities and potentially much more financial gain. Furthermore, even though morning people can be very energetic right after waking, they tend to lose steam faster than night owls throughout the day. Both sides perform equally well in reaction time tests an hour after waking, but after 10 hours of being awake, night owls perform significantly better. Your inner clock is regulated by many proteins which are created from various genes in your DNA. Studies have even shown that a single change of the genetic code near a gene called period 1 can result in an hour difference in your waking time. As crazy as it seems, scientists also found a correlation between these same genes and your time of death. The early risers were more likely to die around 11 a.m., while the night owls were more likely to die before 6 p.m. What about teenagers, you say? It's true, most tend to be night owls due to the hormonal changes during puberty, but this tends to wane out into your genetic default as you enter adulthood. So while there may be some truth to early birds getting the worm, night owls aren't exactly lagging behind in life, they're just lagging behind in time. You may have heard this
disrupt our circadian rhythm. Waking up late, waking up very early because you had to go somewhere, waking up late then rushing to school, sleeping late because you forgot an assignment you had to do. These all could be the possible reasons. So when the circadian rhythm gets disrupted, it means that the body systems don't function optimally. A disturbed sleep-wake circadian rhythm can give rise to serious sleeping problems. Eating in sync with your circadian rhythm is crucial for improving your health. If a person eats out of sync of this rhythm, then they may be at higher risk for cardiovascular diseases, diabetes, and obesity. This is the reason why at sometimes we feel more hungry than ever. In this online school pattern, we may feel hungry during classes, and therefore we are tempted to eat that time every day. It is based on when you eat and how often do you eat. A study of mice determined that eating whenever you want without regard to your biological clock can lead to metabolism disorders. This includes obesity, which can lead to type 2 diabetes, and hyperlipidemia, which is high levels of fat proteins in the blood. Eating in sync with the circadian rhythm can reduce the risk of having type 2 diabetes, cardiovascular, and other metabolism disorders. To ensure the healthiest lifestyle, consider the times you're eating and what you can do to normalize your patterns. On the topic of this disruption, let's see what happens. What are the symptoms of circadian rhythm disorder? There are many symptoms. Here are just a few which we have listed. Difficulty in falling asleep or staying awake, daytime sleepiness or sleepiness during work shift. This usually happens in the modern world when most of our time is invested during the day working and at night relaxing. Although, if we have no regard for our circadian rhythm, this can cause these problems. And you may even fall asleep during the class, which is not a thing you want to do. You also may feel fatigued, exhausted, tired, and maybe demotivated to do any sort of work which you really need to. It also causes difficulty concentrating, which may be during your classes, during work, during presentations, anytime actually. It also decreases the alertness and lack of control over the emotions and the mood. This can also cause headaches, digestive problems, and other symptoms. So, treating disruption of or normalizing the circadian rhythm can take some work and discipline on your part. And yes, as the question presented in the chat, it is possible to manipulate by the external factors and it is possible to change your habits. So, here are some of the things which you can do. First of all, you can manipulate light. Manipulating light is one of the ways to normalize the circadian rhythm. Light, mainly blue light, which a lot of people talk about, a lot of new lenses are coming to avoid blue light. It is a big topic nowadays. It's responsible for signaling your body when it should be awake and when it should be asleep. Blue light is part of the sun rays which come to us and is produced by the sun, and it is naturally found in the brightest part of the day, as mentioned. Therefore, blue light during the day is good, but artificial blue light, which is caused by devices, any kind of device per se, especially during the night, is bad for your circadian rhythm. Maybe watching that series at night wasn't the best thing to do. So now let's see how you can treat the disruption of these circadian rhythms. Fast and normalized meal times. This is another very good method. As you have mentioned earlier, eating in sync with the body's circadian rhythm can help you treat a disruption of the circadian rhythm. If you're traveling across time zones or getting jet lag, then you may need to fast a little bit so that your body gets back and reworks the entire clock. Or else it's going to be very difficult sleeping at night and waking up in the morning. Next slide, please. Chronotherapy. Chronotherapy is discussed earlier and is described as making gradual changes regarding the time you go or wake up. This requires major behavioral changes and is not recommended unless you totally need to. It is a very difficult process and may require a lot of time to do. This is very beneficial if you will have to change your cycle, maybe moving to another country, maybe you got a different shift at work. It depends actually. So for this, you need to have a lot of different changes. And the most important of all of this is the time you sleep and the time you stay awake. If you are sleeping and staying up till 2 o'clock, maybe even 3 o'clock, doing some work, watching some movie, it depends actually. You want to change it. It will require very slow and gradual changes over days, weeks, and even months. What you need to do is decrease the time you go to bedtime. For example, you may go by like 11:30, 10:30. You want to basically want to reduce the time you are staying awake and increase the time you're sleeping to do so. For this though, they need to make changes earlier as well. They need to complete their work, they need to eat their food so that the body doesn't feel anything is deprived of.
So, let's now summarize what we have learned during this session. Circadian rhythm is a 24-hour internal clock. The area of the brain called the hypothalamus controls each person's circadian rhythm by receiving signals from the eyes that report when it is daytime and when it is nighttime. The hypothalamus, in turn, controls the amount of melatonin released to correlate sleepiness with darkness and alertness with lightness. More than 100 bodily functions and behaviors follow circadian rhythms. Physiological and psychological and all vital life functions fluctuate based on it. Light from the electronic devices at night can also confuse our biological clocks. Some individuals identify as early birds or larks, as they can do the most difficult tasks in the morning, while some persons are night owls, working best in the late evening hours. Knowledge of what type you are can increase your productivity and creativity. Changes in our daily rhythms, such as those caused by jet lag, night shifts, and daylight saving time, affect most people, but are particularly difficult for teenagers. Between childhood and adulthood, the timing of sleep changes drastically. Puberty and adolescence can also cause a jet lag of sorts, where teenagers find it very difficult to wake up in the morning. This is called the social jet lag. All of these disruptions in the circadian rhythm affect the body and the mind, and they may lead to sleeping difficulties and reduced alertness. As has been rightly said by Mark Sisson, I have few absolutes in my routine, but one of them is I honor my circadian rhythm. The pleasure I get from consistently sleeping well trumps anything that would disrupt it. And these are some of the links that we use to create this PPT. Now let's end on a lighter note. You now know what excuse to give your teacher when you're late to school.
Thank you so much, Deepti ma'am and her team, for providing us such a nice experience as well as exposure to theoretical and empirical knowledge. Now we have some questions coming out for you guys. So the first one we have is, since the circadian rhythm can be manipulated by external factors, it must be possible to change our habits using these possibilities.
Yes, so I actually answered this question even during the presentation, and I'm going to answer it again now. So basically, it is possible. It is very well possible. It's not to say it is easy, but it is possible to do it. Maybe changing your sleeping times, changing your diet, completing your work beforehand. And if you want to watch a series, please watch it during the daytime. Please do not mess up your circadian rhythm.
Okay, so we have one more, and we don't know if it would be good to go here, but then if any of the presenters would like to take it. So it's from Himaksh from grade 6. I'm a night owl, one doubt. I have this thing in my mind when I'm sleeping. Every day I dream of a future picture. I mean, when I'm sleeping, I see this picture of future. Is it true to see future?
Uh, would anyone like to answer that question? Grade 9?
Yes, ma'am. So
Please go ahead.
basically, this is out of the scope of our presentation, but I'm still going to answer it. This is basically vision. Our mind is very creative. Maybe it is the future, we don't know yet, but our mind is very creative and can imagine a lot of things. We can't say for sure it's the future, but there are many theories on visions and everything. So that is a thing that is of future research. Like maybe it is. We have to see. Only time will tell.
Yeah. Uh, Soumya, you'll have to unmute yourself, beta. We can't hear you.
Yes, ma'am.
Yeah.
Thank you, ma'am. So sometimes all we need to focus and enjoy is a break. So guys, अब हम आपसे विदा लेते हैं, लौटेंगे एक छोटे से ब्रेक के बाद.
तो तब तक के लिए बने रहिए हमारे साथ एंड कुछ पलों में ही होगी हमारी फिर से मुलाकात. So just a 10-minute break and we will be back here after 10 minutes. So let's.
Can I just announce one thing to audience with your permission, Soumya?
Yes, ma'am.
So this is very important that next session is Dr. Akash Sinha's on Surya Siddhant, and he is going to connect philosophy and science together, and it will be one of the very enriching session like this session conducted by Gurgaon students. We are honored, Dipti ma'am. We are honored to have Gurgaon students, and they are so good. And when we were watching the quiz, we saw that somebody was asking question on YouTube, and impromptu kid was taking the question from chat box and replying. Yes. So welcome to Carriers Children with Dipti ma'am, and obviously different mail, and we going to share the appreciation letter also. Thanks a lot, ma'am.
Thank you, ma'am. Thank you so much.
Also, Dipti ma'am, because there are many schools which are watching also, it's a request that if we can take an extensive session on this, because this was very informative.
Yes.
Maybe in month of January, Feb, evening session with carriers.
Yes,
so that
ma'am.
will be
You
great.
tell us. Yeah. We'll be open to that, ma'am. You let us know the details. We will be open to conducting a session.
Yeah. Thank you so much.
Thank you. Thank you, everyone. Have a nice day.
Thanks a lot, ma'am.
Thank you,
a lot, Ekam and all. You were just too good. Par excellent.
Thank you, ma'am.
So a big clap to all 4 kids.
Yes.
Of Gurgaon. And I will be coming once in a week to Gurgaon, Dipti ma'am. I would love to meet you.
You're more than welcome, ma'am. Anytime. I'll be happy to meet you. Yeah. Thank you so much, ma'am. We will take your leave. Thank you.
Yeah, thanks. Himanshi, Gulfam sir, we have shared a YouTube link of grade 11 students who have made such a beautiful,
Yes, ma'am.
so maybe we can showcase that. once now.
So
Yes,
we are going
ma'am.
to meet.
During break time. We will join sharp at 11 a.m. for Dr.
Sure,
Sinha
ma'am.
Vimansi.
Yes.
Vivasvat Savitr Bhargo Devasya Dhimahi Dhiyo Yonah Prachodayat.
O glorious Sun, giver of energy, remover of sins and ignorance, bless us with consciousness and let us be infused with the glow of knowledge. So says the Rig Veda, a holy book that emerged from the Indian subcontinent and also the foundation of many of the cultures that have emerged from here.
While the sun is no longer considered to be one of the greatest gods here, its importance in our lives is constantly brought up in songs, stories, and in various forms of worship. There are many stories about the sun in all his glory that emerge from here. Here is one which explores the sun as the ultimate truth and asks the question, can we handle it in all its dark glory? And what if we cannot?
Surya was a faithful and a devoted husband, but his wife Sanjana couldn't bear being near him. The problem was that he shone so brightly she couldn't look at him. So one day she asked her maid Chaya to secretly take her place and she slipped away to earth to live anonymously in our world. Chaya enjoyed posing as the queen. She even had a son with Surya, Shani, the planet we know as Saturn today. He was slow moving, rather glum, and not very bright at all. But still, Chaya doted on him and neglected all of Sanjana's children. Finally, Sanjana's children had to report this to their father. Mom, Mom isn't just herself anymore, they said. She ignores us and she only plays with Shani. Surya's suspicions were aroused. So when he got home at the end of the day, he would watch her closely. And sure enough, she was only a shadow of her old self. Eventually, he realized, to much of his shock, that this wasn't his wife at all. Who are you? He said. What have you done to my Sanjana? Chaya was terrified. Surya usually glowed with magnanimity, but at times like this, he could be formidable. So she told him the painful truth that his wife had found out that his presence was unbearable and had deserted him. Surya rushed down to earth to seek his beloved love. He found her trotting in a pasture as the form of a mare, so he took the shape of a stallion and ran after her. But Sanjana wasn't eager to return to heaven. You hurt my eyes, she said. You shine too bright. In hopes of persuading Sanjana to take him back, Surya enlisted the help of his father-in-law, Vishwakarman, the great architect whose masterwork is our universe. Vishwakarman tried his best, but Sanjana, she was adamant. She was adamant of staying on earth where she was comfortable. Finally, Vishwakarman came up with the perfect plan. He invited the sun to lie down on his lathe and carefully sawed away much of Lord Surya's light. Then he sent his part down son in law to Sanjana, where she caught the sight of her husband where she could scarcely believe her eyes. She said, You're the most beautiful man I've ever seen, she exclaimed. The dazzling couple returned home and lived happily ever after.
Session. Um, Now over to Himanshi and Soumya to take it on from here.
So, once again, welcome to the day 2 of Educational Bootcamp.
Surya Siddhant is the first among the tradition or doctrines in archaeoastronomy of Vedic era. In fact, it is the oldest ever book in the world which describes Earth as sphere but not flat, gravity being reason for object falling on Earth, etc.
Huh? What are you talking about? I'm not getting it. Yeah, I know Surya is for sun, but what is this quite complex term, Siddhant?
Wait, Imanshi, all your queries will be answered soon. We are pleased to welcome a very inspiring science educator, Dr. Akash Sinha from Department of Electrical Engineering, SNU today to discuss Surya Siddhant.
Ma'am, you are muted.
Before you start, Dr. Sinha would like to listen few words from our Shashi ma'am and Matthew about Surya Siddhant. The session what you are taking, we are connecting science with our value system, which was written, no, before Christ, so many years before Christ. So over to you, Matthew. Would you like to share your view on Dr. Sinha's philosophy of connecting science and philosophy together? Thank you.
Well, can I thank him first for presenting? It is exciting to have someone that actually will show to our students that we don't live in silos of learning domains, that science, philosophy, and other domains is all together in our learning journey. And again, I'm very grateful for him to be able to give this message across to our students. And I hope our students will follow that passion because, as I've said many times, many of them are doing personal projects that look at some of the big questions we ask of ourselves in our world today. We follow the United Nations Sustainable Goals. We're looking for solutions. And science, philosophy, our values, all these things generate these solutions and are important for our well-being. So thank you, Dr. Sinha, for being here. It's an exciting experience for our students to be able to listen to your views and for them to be guided about their learning journey. So thank you and welcome.
So I think Dr. Sinha can start. I can see Sasi ma'am busy with other meetings.
All right. Thank you so much, Vinita ma'am. Thank you, Matthew. It's great to see you're always interested in all the education endeavors from all angles. And thank you, Shashi ma'am. Great to be part of this. And I'm very excited to hear from Soumya and Himanshi, the young little kids who are so excited and putting forward things in such nice manner. So really happy, looking forward to this. So what I'm going to do, I'll have a small presentation, but although I'll mostly talk about it. And just give me a moment. Let me try to share my screen.
That
Yes.
moment, Shashi ma'am would like to share her views on Surya Siddhant, your session. Very close to our heart, philosophy, mythology, and science together. Shashi ma'am, can you please add 2 lines for Dr. Sinha?
I'm just overjoyed, Dr. Sinha, to see you. And I was sharing with the people sitting around me here in our meeting room who are all looking at you and waiting to hear from you how inspiring you've been all through this journey, and our first meeting where it struck me that you have this dream of doing something different, reaching out to students in a very different way, beyond boundaries of any physical wall or institution. So, a hearty welcome, and we so look forward and cherish this association that we have. That's all I have to say. Thank you.
Thank you so much, Shashi ma'am. It's always very encouraging to hear from you, and always very excited to get involved with students, whether at the college or university or school level. And I hope can at least bring some inquisitiveness to their minds of See, it's one of the things is that with science and philosophy, it seems, you study civilizations across the world, and you will see that there are pieces of science that, suddenly appear from nowhere. And it almost seems like we have these gaps in history. Nobody knows how the pyramids of Giza were built, or nobody knows, how Mayan calendar had some very accurate predictions. And similarly, I think Surya Siddhant is one of those things. It's a book that I read a couple of years back. I had been researching about the ancient Indian sciences, and I was quite surprised when I learned about it. So we'll be happy to share some of my views there. So let me share a few slides for today. All right, just let me know if you can see the.
Yes, sir, it's visible.
All right, great. So, so as I said, Surya Siddhant it's an ancient book of Indian astronomy. It literally means the principles or the theories on the sun. And when we say sun, I think it encompasses sun as the entire solar system. So the entire solar system, how it functions with sun, in the center. That's what Surya Siddhant is about. And so as I said, I had just read this book, although the book had so much mathematics that I couldn't quite read all the details, but I got a gist of it and wanted to present some of that in front of you. Okay. So what it is that as I said, it's a book on ancient Indian astronomy. This book, I was surprised to see it's full of equations. There are like tons and tons of equations there, lots of algebra, lots of geometry, lots of trigonometry, infinite series. So it's actually more mathematical than a standard textbook that you'll find in science and astronomy. So that was one big revelation. Another big revelation was that people have tried to estimate how old it is, when it was written. And there are different estimates. Some estimates say that it was done in like 580 CE. Some estimates say it was 2000 BC. But a more recent estimate, which was presented by Professor Nilesh Oak at Oxford University, is that he found astronomical references in the book. So, for example, you look at the night sky today, and there's a certain pattern of constellations that you will see. Now, if you look at that pattern, you will be also able to tell today's date just by looking at the pattern of stars in the sky. At least the year you'll be able to tell. So Surya Siddhant records in the book itself, there are dozens of astronomical observations of that day when the book was being written. And surprisingly, all of them actually point down to pretty much a single date, which is almost 14,000 years back. So this is actually a fairly strong evidence. If you have a dozen or so astronomical observations all pointing to one single year. So it's actually a fairly strong, because, otherwise there's really no way to kind of date them, because a lot of this knowledge used to get transferred in Guru Shishya Parampara, when, it used to be transferred verbally from generation to generation. And so, it is surprising that something this sophisticated was written about 14,000 years ago. And I say this with confidence because now there seems to be overwhelming evidence to support that. The book is fairly small. It's just 500 verses. And if a verse is like a couple of lines, or maybe 4 lines in some cases. And so, 500 verses, you can probably fit in 10 pages, or maybe 20 pages. So it's actually more like a book of formulas. It's like when you're in school and you have, let's say, if you have a maths exam, maybe you have a little, booklet, which is a booklet of formulas. So it's a bit like that. It's full of very concise, very precise formulas, observations. It's almost like a reference book. It's like a little reference book of astronomy. So anybody who's an astronomer would probably be using it in the ancient time. There also, in the Surya Siddhant, there's a story that this, all this knowledge was first revealed to Mayasur. It was revealed to Mayasur by the sun god himself. So that's kind of, that's a part of the story. But Mayasur also happens to be father-in-law of Ravan. And what is interesting is that, similar astronomical observation dating of Ramayana has been done. And it is found that, Ramayana probably also happened 14,000 years back. So so it's really nice to see that there's a coincidence, if you call it a coincidence, that Surya Siddhant, the dates of Surya Siddhant and the dates of Ramayana match up, at least based on astronomical observations. So just like in Surya Siddhant, Ramayana also has a series of astronomical observations in Valmiki Ramayana. And from there, you can actually deduce the date on which Ramayana happened. And so though these two actually come close by, and there is, when there's a cross-reference to Mayasur, who's the father-in-law of Ravan, he's the father of Mandodari. He's supposed to be the, great scientist and architect who built the entire Lanka. And so that's kind of the story part, but the story also mixes up with the actual observation. So there's more to be explored here. So anyway, that's a little bit about the book. But what's really the big deal? So the big deal is, as Himanshu pointed out, 14,000 years back, it still describes Earth as a round sphere. In fact, there's a chapter on it on Bhugol. So Bhugol literally means the Earth is round. Even now, if you're studying geography, and the Hindi word for geography is Bhugol. There is a verse from which you can actually deduce Kepler's law of planetary motion, which is also very interesting. So for some of you who might be familiar, Kepler's law of planetary motion is what governs the orbits of planets around the sun. And it tells you that, all these orbits are elliptical with sun on one of the foci. So, similar deduction can be made from one of the verses. It also describes gravity as a force that attracts things towards it, although you don't quite find the formula for gravity. But it does mention that there's a gravity or Gurutwakarshan force which is actually pulling everything towards the earth. You find Pythagoras theorem in it, infinite series, lots of trigonometry. In fact, you also find infinite series of trigonometric equations with sine, cosines, and so forth. Lots of polynomials, squares, square roots, cubes, so forth. So so it's just that to be able to know all this knowledge almost 14,000 years back is fairly surprising. Or even if it was a few thousand years, I still think it's kind of surprising, and we are probably missing a link in the history. Okay, so also there are some fairly accurate calculations in the Surya Siddhant. And there are calculations which estimate the speed of light. There are calculations that estimate the diameter of Earth, diameter of Moon, diameter of Sun, and planets, including Jupiter, Saturn, Venus, Mercury. There is no mention of Uranus, Neptune, and Pluto. But for all the planets that are visible from naked eye, you're able to find their diameters. Also, there's very accurate description of time period of the planets. So how much time the planet takes to go around the sun. Fairly accurate description of the elliptic geometry of orbits, which also tells that they knew about Kepler's law of planetary motion. And then a reasonably complex subject, which is a precession of Earth, where our Earth, most of you students will probably know that it has two basic motions. One is that it revolves around its own axis, rotates around its own axis, and the second is that it goes around the sun. It does one revolution around the sun. Now there's a third motion, which is a bit like, motion of a top. So if I could just use this mouse and say, so a little bit of this, like a top. And in order to do this kind of a top type motion, it takes about 26,000 years to complete this one cycle. And this is also fairly accurately described. Now, this is also something, fairly complex to understand and predict. So, and most of the calculations come, fairly accurate compared to the modern calculations. There are also precise formulas given as to how you are estimating things like diameter and elliptic orbits and so forth. So I'm going to take a couple of examples from the book as to what, meanwhile, if any students have any questions, we can always take them at the end of the talk, or even, in the middle of the talk. It's fine. Huh? So feel free to ask or put it in the chat window. I know many of our students are on YouTube, so maybe there is. Okay, so we can take them at the end of the session. Great. So anyway, I picked up one of the, it's verse 12.53. The chapter itself is called Bhugol Adhyay, which means, as I said, Bhugol means the round earth. Bhu is for earth and Gol means round. So what this verse says, and how it is telling you that Earth is round, it's saying that everywhere on the surface of the globe, people suppose their own place to be higher than that of others. Yet this globe is in the space where there is no above nor below. Okay, And this is the kind of thing you will get. And then there are verses, a couple of verses before and after it, which also emphasize how it is round. Not only it says it's round, there's also a very precise definition of latitude, longitude, of Earth, circumference of Earth. All these calculations are there. But this verse sort of summarizes when you had to, let's say, explain to a layman, because in general experience you might unless you know a basic astronomy and geography, people might say that okay, Earth appears flat, so it's probably flat. In fact, I don't know if you know that while we had this knowledge, whatever 12,000-14,000 years back, I was actually surprised that there is a society of flat earthers. I don't know if you know, there's a society of flat earthers who still believe that the earth is flat. But when you look around on the earth, you can get that experience. You might feel, yeah, the land appears flat. And if you think that you're on the flat part, then you will, always feel this, because the earth is spherical. Any other part of the region, especially if somebody is standing far away from you, obviously due to the curvature of Earth, they will appear at a lower height. And this is what Surya Siddhanta is trying to emphasize in one of the verses. Another piece that I want to tell you is that, this latitude and longitude that we've drawn on Earth, they also took it and made it into in the space. So you can extend these latitude and longitudes from Earth into space around the Earth. And then in those latitude and longitude, you can describe the positions of stars, constellations, planets, and so forth. And this is also a system that people still use even today. But this kind of a geometry is also done in Surya Siddhanta. Now, this is one more verse, and I'll just read out the translation. It essentially summarizes Pythagoras' theorem, and so it says that the square root of sum of squares of the this is a Sanskrit word for gnomon or gnomon, which is the sort of the base, and then the shadow is. So this is actually describing an astronomical instrument, where a shadow is formed, and the shadow is the hypotenuse. And if you take the square of it, and then from it you subtract the square of the other part, then the square root will remainder is the shadow, which is essentially another way to basically put forward the Pythagoras theorem. So you all remember Pythagoras theorem is a square plus b square is c square, and in some sense they're saying that essentially they're saying the same thing. And so this is one more reference, completely independent reference of how we knew about Pythagoras theorem. Now, one more interesting reference is, and for some of you who might have studied Kepler's law, this is again, you'll find in chapter 12, verse 46, where it actually tells about that the time taken by Earth to move this, to move in this area, which is r theta, when it is close to the sun, at the peak of Grishma, which is the summer solstice. So it's not exactly the it's not exactly the local seasons, but summer solstice of the sun, along with the periapsis, and it is slower along apoapsis. So it's essentially telling you that as the Earth gets closer to the sun, it moves faster, and as it goes away from the sun, it moves slower. Although these areas are equal to r theta. In both the cases, the areas are equal to r theta. But it will take, it will move faster when it is closer to the sun, and it will move slower when it is farther from the sun. And so if you see what Kepler's law says, that basically all the planets move in elliptical orbit, and they take equal time to cover equal amounts of areas. But when you're closer to the sun, it will take, you will move faster. So even though you are covering the same area in equal amount of time, the speed when you're closer to the sun is faster, and the speed when you are farther from the sun is slower. And now this very much summarizes the Kepler's second law. And the third law is basically derived from the first and second law. So in some sense, you can see that Kepler's law is also something that was well known in the times of Surya Siddhanta. Now, this is about things that we already know. Now, I was looking for something that maybe, because see, the science, doesn't have to be linear. It is possible that we knew something back then that we still don't know. And I was trying to see if there is something like that in Surya Siddhanta. Now, I did come across one strange prediction. And this prediction was that the sun, is a binary star. It has a binary companion, and then if it is a binary companion, it's likely a black hole. Now, this likely a black hole is not given in the Surya Siddhanta. This is something that, in fact, I just tried to do in my own free time. In fact, I've been doing a little bit of research in this. And so I deduced that if sun has a binary companion, it is likely to be a black hole somewhere in the beginning of the Oort cloud. So if you know what the Oort cloud is, from where all the distant comets come. And the Oort cloud is in the region of around 0.03 to 0.3 light years and so forth. And then it also stretches beyond that, but it sort of starts in that region. And this is the region where it is, at least according to Surya Siddhanta, there could be potentially a black hole in that region. And the sun's time period is 26,000 years. This time period of 26,000 years is also known as a Chatur Yug or a 4-yug cycle. And so the time scale of sun's orbit is defined into 4 yugas. And each of the yug, it starts from Satyug, then Treta Yug, Dwapar, and then Kal Yug. And then, their time duration doubles from the previous one. So that was another interesting observation, but it also tells you that we know that the sun's orbit is elliptical. Now, these claims are yet to be confirmed or rejected. I did read about, there are some theories about sun's evil twin, and so forth. But I, if some of you were to take up or look up Surya Siddhanta, I'm sure you will find many other such predictions. And one of the good ways to understand whether an ancient science was correct or not is one is to compare with what we have today, but the other is that there could be instances of things that are yet to be known, but it's given in that book. And I thought this was one of those things. And so, maybe one of you will take this up and try to figure out if this is there. So something for you thinking minds to look at. So that's kind of pretty much on my presentation today. These are a couple of references, mostly the ones that I used for this presentation. So there are talks on Surya Siddhant. There are papers written by several people, but Professor Nilesh Oak, I believe he's from Dartmouth University in US, Institute of Indic Studies. He's done a series of talks on this, and one of his famous talks was done at Oxford. A lot of the data that I presented here is based on his talk. It's available on YouTube. You can look it up. And then the Surya Siddhant ebook, especially if you want to read an English translation, it was translated by one of the Britishers in about almost 100 years back, and so that text is also available online as PDF. And then you also have the Surya Siddhant book available on YouTube, on Amazon, and it's available in Hindi, English, Sanskrit, so forth. So anyway, that's pretty much about the talk today. I am very happy to take up questions. Thank you. While the stars will pretty much appear fixed with respect to Earth's motion, they will almost move like an entire sky in one go. The planets and the moon, they will actually be seen moving across the sky. So that's one way to differentiate here.
Ramya, will you read the question? Dilshin is the name of teacher. Another question was there last time. So can you please read the second question by a student, I think it's a 6th grader. Yeah.
Yes, so here is the second question. As teachers, how can we inculcate a mindset in students which lets them think and observe the way our ancestors in ancient India did, even in the absence of advanced technology?
Okay, this question is from teacher, sir.
Oh, acha. Well, so I thought Dilshin was a student. So thank you, Dilshin, madam. I think you're asking very good questions. So, part of that, this is what we are trying to do. I think these kind of activities like celebrating the sun, where we don't restrict ourselves just to, the curriculum, the textbook, which is also important. Let me, emphasize that for all the students, please don't, it's important you learn your curriculum. Only then there's point of going beyond the curriculum. But having said that, I think this is the kind of activity, because a lot of these things, so they were probably being taught thousands of years back, but we can't suddenly introduce them into our system. It's going to take a lot of effort. Nevertheless, we could have an event like this where boundaries are opened, and then openly we share information openly, and then we let students explore. For example, there are a couple of references that I put in the talk. Students, teachers, they are free to explore it and come back. We can have a little more discussion on this, and we could have similar sessions on other aspects. And so, till we get it back into our system, obviously, ideally, we should be sort of really relooking our ancient history. I think there are a lot of pieces which are extremely puzzling and need to be relooked. And I'm not saying that from the point of view that, okay, just because I'm an Indian and we're all Indian, so, we must always have to be proud of everything. No. It's, in fact, I was myself surprised when because most of the ancient texts that I read, they were never mathematical. Although that, for example, all these texts are great, whether it is Ramayana, Mahabharata, Gita, Upanishad, but I had not seen anything similar to what we do in modern science. And I was thinking, why is this gap? And so I was quite surprised when I looked at Surya Siddhant. And in fact, after looking at Surya Siddhant, I realized that there's actually a whole class of books in our ancient studies, and they are all called as Siddhant. So there is Surya Siddhant, there is Siddhant Shiromani, I think there are a couple other Siddhant in name of sages. And all these Siddhants are actually very precise mathematical books. And it's just one of the pieces that I was just surprised, thinking that even though I was interested in ancient Indian studies, I had been looking with an open mindset, I still couldn't come across them until very recently. And so you are right that we need to create a culture that at least exposes our students that, yes, let's look at the modern, let's also look at the ancient. They can both learn something from each other. So yeah.
Thank you so much. Over to you, Soumya. Before you guys speak, Dr. Sinha, I was just listening to you, and definitely I'm going to read this book. Also, I was thinking that, maybe...
Oh, ma'am, you will enjoy. You are physics teacher, no? I don't know about Dilshin, madam, but...
also science teacher.
Oh, cha. So yeah, absolutely. Even non-science teachers would enjoy it, but it's just that it is so much mathematics that if you don't have a science background, you might get a little turned off because there's just lots of equations there.
So we'll have with all maths teacher once, maybe next year sometime when you are free, in the coming months, especially for maths teachers.
Absolutely, yeah, absolutely.
Thank you so much. Over to you, Soumya.
Thank you so much, sir. Your session does prove that indeed somewhere something incredible is waiting to be known.
Perfection is not attainable, but if we chase perfection, we can catch excellence. So, guys, it's quiz time. Time for excitement and competition. Are you all ready for the battlefield of questions to begin?
Yes, we are. This mind sport challenges us, tests our knowledge, and encourages us to keep learning. So, on this note, I request Angad and Pranil to take it further.
Before you start, Angad and Pranil, it's very important to note that your time is, you have prepared beautifully, and 15 minutes quiz. So smartly you guys start, and we are going to participate. Introduce yourself, your name, your school, then you start. Thank you.
Good morning, everyone. Today, I am Pranil Munshi of grade 9 Ranthambore from Shiv Nadar School, Noida, along with Angad Singh Marwa of the same class. We'll be presenting a quiz today. So, Angad, could you please share your screen? The quiz will be about the sun and also will include questions from the various activities and interactive sessions that were conducted during the EBC.
I'll just be sharing my screen now. So I would request you all to join on this link with this code 714487.
Yeah. Yes. Angad, can you just go to or share via and copy the link in the chat box and paste it here? Thank you.
Actually, I can't access the chat right now.
You can go back to your Zoom's your Microsoft Teams window. Just press Escape and you'll be able to.
Ma'am, there is no chat window in MS Teams for me.
Just give me a moment. I think people have started. Just give me a moment. Angad, can you stop sharing for a second and quickly paste it over email and send it to me? I'll put it in the chat if you're unable to. Yeah?
Yes, ma'am.
Thank you, Himan. Thank you, Himanshi. We'll just use this. Yeah.
So till technical glitches we are trying to cover up. Can you a little bit speak about the quiz, what you planned, Angad? What is the theme of your quiz? Over to you, Angad.
Yes. So our quiz
You
is
unmute.
yeah. So our quiz is based on questions based on the sun and all the various sessions we have had in this month-long event, which included the session on solar PV output and components of light. So if you have paid attention to the events, you'll be able to answer the questions very easily. And we also have many questions based on sun in general. So hope you enjoy the quiz. The link has been shared on the YouTube channel as well. So please join in quickly so we'll be able to start.
You can tell about your journey of engaging yourself in careers work. Till Wilson ma'am is trying to paste that link in message box. Over to you, Pranil.
Yes, so like many of you, even I attended many of the sessions of the EBC. So my favorite one was the solar PV output one, which Angad just spoke about right now. So there are a few questions from that session, and if you like he said, if you were attentive, you'll be able to answer all of them. So yeah, that was my favorite experiment of all of them, and I also enjoyed the rest of them. Hope you did the same too. So I guess ma'am will just place the link on the.
Yes, we place this link. If you can also share the direct link, we'll place that as well. But anyway, we've pasted the code and the quizzes link. Himanshi has done that. But thank you, Himanshi.
So you can start. Please go ahead, Angad and Pranil.
Yes, ma'am. Ma'am, we have like maybe we can wait for some more participants to join. Then we'll start.
पॉज ज़्यादा ठीक नहीं लगता है ना.
I guess we should start now, as we also have time constraint.
Yes, Angad, we can begin and others may keep joining in through the
Yes.
quiz.
Which element makes up the largest portion, roughly 74% of the sun's mass? Okay, time's up. The answer was hydrogen, and that's the leaderboard. Let's move on to the next question now.
So what is the visible surface of the sun, which is the lowest layer of the sun's atmosphere called? Chromosphere, photosphere, thermosphere, or stratosphere? Alright, so the correct answer was the photosphere.
Okay, so this is the next question. Which is the topmost layer of the sun's atmosphere? Is it chromosphere, thermosphere, ionosphere, or the corona? And time. So the correct answer is corona. Let's see the people who've done it right. Okay,
So a
that's
quick
really
fact,
great.
the sun has four layers. Firstly, the photosphere. Second is the chromosphere. After that, there is a transition layer. And the topmost layer, as we mentioned right now, is called the corona. Okay, so what is the approximate surface temperature of the sun? Sorry for the typo. Um, yeah, so the options are 300 Kelvin, 3000 Kelvin, 4000 Kelvin, 6000 Kelvin, or 8000 Kelvin. Alright, so the correct answer was 6000 Kelvin.
Okay, so that's the next question. Which generation of stars is the sun a part of? Is it population 1, population 2, population 3, or population 4? 5, 4, 3, 2, and time. So the correct answer, that's the leaderboard now. Only a few people got it right. And the right answer is population 1.
So it shows that the sun is not really that old.
Yes.
It's part of the newest generation. So what was the sun and the rest of the solar system formed from? A black hole, the solar nebula, the Oort cloud, or the Kuiper's belt? You have 5 seconds left. Time's up. So the correct answer was the solar nebula, which most of you got right.
Okay. Here's the next question. Who had first suggested the heliocentric model of the solar system in the year 1543? There are two models, heliocentric and geocentric. Who first suggested the heliocentric model? And your time's up. So let's see the leaderboard. Okay. And the right answer is Copernicus.
So the next question is, which spacecraft was launched by NASA and the European Space Agency in 1995 that currently observes the sun's activity? The Parker Solar Probe, the Solar Dynamics Observatory, the Solar and Heliospheric Observatory, or the Solar Terrestrial Relations Observatory, or STEREO. So time's up, and the correct answer was C, which is also known as SOHO, Solar and Heliospheric Observatory. Most of you got it right.
So what is the outflow of gas from the sun's corona called? Remember, corona is the outermost layer. So what is the outflow of gas? Solar gas, solar wind, or corona wind? And your time's up. Let's have a look at the leaderboard now. So a few changes here and there. And the answer is solar wind. Few of you got it right, so it's fine.
Right, so the next question is a true or false one. So the sun is the largest star in the Milky Way. True or false? And your time's up. So the correct answer was false. And let's see how many of you. Yeah, most of you got it
So
right.
there are many more stars like Delta, Sirius, Vega, which are larger than the sun. Moving on to the next question. It's a true or false question. Is sun stationary in space? True or false? This is a trick question. Pay attention, take your time, and answer. And your time. So the right answer was false. It is not stationary. And okay, a few of you got it right. In fact, most of you got it right. That's great. So the sun is actually not stationary in space. It keeps moving, And therefore, if you see all the planets form spirals around the orbit, around the motion of sun in space.
So the next question is, how many stars are there in the solar system? Is it 1, 8, infinite stars, or what number is it? Oh, 1 times 10 to the power 8 stars. Alright, so the correct answer was 1 star.
The only star in our solar system is the sun. That's the next question. Light from sun reaches Earth in approximately 16 minutes, 23 minutes, 2 minutes, or 8 minutes. And time up. The correct answer was approximately 8 minutes. And now that's the leaderboard. And great, most of you got it right. Almost everyone got it right.
So this question is based on the EBC session, and it asks, what does a multimeter measure? Is it voltage and current, voltage, current and resistance, current, heat, energy and resistance, or is it temperature and voltage? So time's up. Chaitanya still leads. And the correct answer was B. Let's go on to the next one.
Okay, so this is one more question based on the session. Intensity of solar PV output or solar photovoltaic output increases with shorter distance with light source. Is it true or is it false? Density increases with shorter distance. And time's up. The correct answer was true. It does increase with shorter distance. And okay, the leaderboard remains same. And almost all of you got it right.
So the next question is, more solar energy means more resistance, so more PV output. Is this true or false? And even this question is based on the EBC session. You have 5 seconds left. And your time's up. Let's see the leaderboard. Alright, so the correct answer was true. And 5 of you got it right.
Moving on to the next question. Light travels in the form of dash and dash. Light travels in two ways, dash and dash. So it photons and waves, photons and energy, waves and energy or heat and light. 3, 2, 1, and time. The correct answer was photons and waves. Let's see how many got it right. What's the okay, remains the same. And 4 of you got it right. So it's not waves and energy. Light energy itself is how light carries photons and waves.
So water is dash and oil is dash. Even this is based on the EBC sessions. So first option is non-polar and non-polar. Second is polar and non-polar. Third is non-polar and polar. And the last one is polar and polar. So your time's up. So the leaderboard has changed. And the correct answer was polar and non-polar, which most of you have got it right.
Okay, so that's the next question. Head of soap molecule is non-polar and tail is polar. Soap molecule has two parts, the head and the tail. So the head is non-polar and the tail is polar. True or false? 3, 2, 1, and time's up. Let's have a look at the leaderboard now. Okay, so B has come up with list, and the correct answer is false. The head is polar and the tail is non-polar.
Right, so now on to the last question of the quiz. So how far is the sun from the earth? Is it approximately 150 million kilometers? Approximately 2 million light years? Approximately 3 trillion kilometers? Or is it approximately 50 million kilometers? 3, 2, 1, and time's up. Alright, so the correct answer was approximately 150 million kilometers. And so the leaderboard has a slight change. And yeah, so most of you, 10 of you got the correct answer. So congratulations. And now we see the final results.
Thank you, Angad and Pranil, for reviving back our enthusiasm. Now we have Ms. Sonia Sharma, bioeducator, Deputy Science Head from Shiv Nadar School, Noida. We welcome you, ma'am.
Before we start, ma'am, can I have just one line? This is very important, audience, that we will start virtual visit in another 2-3 minutes after Sonia ma'am's, two lines on 2-3 lines. So we are already having scientists and from ITER France. Welcome, sir. We are honored to see you on screen. Over to you, Sonia ma'am. You are on mute.
Can you hear me?
Yes, sir.
Okay. Are you ready? You want me to start, or you have a different piece?
Just 2 minutes, sir. Just 2 minutes. Sonia ma'am, you are on mute. Samyak sir, is there some technical glitches? Should we call Sonia ma'am later on? Yeah, Sonia ma'am, please be there. We'll call you in between. So before we start, there is a very important announcement. Obviously, children are going to welcome you, sir. There is a beautiful video made by grade 11 student on Sun, which we will be displaying, maybe after an hour because you are already there, and we displayed it there, and we specially prepared that video for you, sir. How our students depict sun with a dance, drama, acting. So you will definitely going to like it. So maybe because your session is 2 hours, so maybe in between when you feel that we need a break, we will display that video. Over to you, Himansi and Soumya.
So, so ITER is an international nuclear fission research and engineering mega project which aimed at replicating the fusion process of the sun to create energy on Earth. In addition to contributing to the ITER project as a member of the European Union, France has made and honored a number of specific commitments. France has provided the site for the project and carried out preparatory works including clearing and labeling, fencing, and networks for water and electricity.
I'm personally yearning to take a tour of the scientific hub, and so now it's time to go to ITER.
What?
बेटा
What are you saying,
आज क्या
Simon?
हो गया था? तुम क्यों नहीं बोल पाए?
How are you so sure about it?
Come on, Manshi, think big. It's time to have a virtual tour with Mr. Koblenz, the head of communication at ITER. His past career has crisscrossed multiple sectors. As a US regulator, he coordinated efforts to reform inspection and enforcement practices and applied probabilistic risk models to improve safety at nuclear power plants. At the International Atomic Energy Agency, he worked with Director General Mohammad Al Baradi on nuclear diplomacy in Iraq, Iran, and other political hotspots. He is also the chairman of Cloque, a startup establishing new standards for data security and online privacy. We welcome you, sir.
Thank you. Thank you very much for that lovely introduction. Um, I think it's quite exciting for me also to be coming to you to this educational boot camp, and I see that you just finished a rather challenging quiz. So I think that the students and those watching on YouTube should know quite a lot now about the sun. And I'm going to try to work two bits of magic for you over the next while. The first is to bring you from India here to France so that you have a chance to go with me into the French countryside and see where we are, and then into the buildings on ITER. The second bit of magic is to try to convince you that it's possible to build a sun on Earth, which sounds quite ridiculous or quite fantastic, but it is an ambition that India shares with all of Europe, plus the United States and Russia and China and Korea and Japan. All of these countries working together to try to accomplish this incredible feat. Maybe the most complex scientific experiment that humans have ever done in all our history. So first, let me ask, just to verify, is it correct that we have about 2 hours, not quite 2 hours? Is that the amount of time?
Yes, sir.
Okay, I want to be respectful of the time. So we will, what I'm going to do first is try to share my screen, and you can tell me whether, let's see, whether that works or whether that doesn't. Can you see my screen?
Yes, sir, it's visible.
Okay. So this is where at the moment I am actually in this building sitting here. If you can see my little cursor, this is a staffing building, and this is an international site here in the middle of the mountains surrounding Provence. So this is quite a rural area with rivers and mountains and lots of forests and greenery, and a little bit of some farmland over here. So when I say I'm going to bring you here, I am sitting right behind the window here. So if I look out my window, I can look directly onto this work site. And what we're going to do is to try to take you with me to understand how all of these things, how all of these buildings contribute to the ITER project. And I will tell you, most of these buildings, all of the buildings were built by Europe as one of their tasks for the ITER project. And most of them now are either owned by Europe or owned by the ITER project itself. But this building here is a factory where we're making some giant magnets. And this building is the only building on the work site owned by India. All the rest are owned by Europe or by ITER. And so we're going to go inside this building as well to see what India is doing. Actually, India is contributing here, it's contributing here, it's contributing here, many of these projects. I'll tell you all about that. But to try to explain why countries of the world on 3 different continents are making really more than 1 million components that are all getting shipped here, and then they arrive quite a ways to the south, to the ocean, to the Mediterranean Sea at Marseille, and they get shipped up 104 kilometers until they come to this work site, and then all of them work together to put together this central machine, which is right in here, and all of the support systems. Before I start the virtual tour, I'm going to show a PowerPoint. Before we go inside the building, I'll try to show a PowerPoint that will give you a bit of additional information on how this works. So this is a side photograph taken of the same site. Again, I'm here in this building, and this is the central building, where we're making something called a tokamak. So before I go any further, can you hear me just fine? Okay, good. So here we are for the Indian Youth Nuclear Society Educational Boot Camp. My name is Laban Koblenz. As I mentioned already, we have about 35 nationalities here. I am American. My own background is in both nuclear fission and nuclear fusion. I will be explaining the difference, and as well as communication. So I have a great deal of love for India, for your country. I've been there multiple times, both for ITER and before. I think my greatest claim to or pride in my visits to India was once having lunch after listening to Sonia Gandhi and Manmohan Singh. This is quite some years ago, before your current Prime Minister, when it was Manmohan Singh, and having lunch with him. So that was a huge, big honor. But I have quite a lot of love for India. So that's my background. We'll now go into the actual presentation. Here is another view where, again, you can see all of these flags of the different countries. China, Europe, which includes, of course, the European Union countries, but it also includes, even after Brexit, because, of course, the United Kingdom left Europe recently, about a year ago, under Brexit, but United Kingdom still wants to be part of this project, so they're staying in under Europe, as well as Switzerland. Switzerland is not part of the European Union, but for the purposes of this project, it joins. And there proudly is the Indian flag, then the Japanese flag, the Republic of Korea, South Korea, Russia, and the United States. And this flag is our little ITER flag. Now, why do I keep talking about all of these countries? Because if you listen to many of the challenges that your generation faces, right now we are all facing the challenge of COVID, the pandemic. We are also constantly talking about climate change. We talk about, of course, insecurity associated with poverty, or with food supply or water supply, fresh water supply, energy, etc. All of these challenges, humans have used technology to try to fight, to try to face these challenges. In most cases, when we discover a new technology, we want to use it. The natural inclination for humans is to use the new technology for me, for my family, my clan, my country, my allies. So it seems very strange when you look at all these flags, because in the news, if you read the normal news cycle, you will often see things like maybe India having a dispute with China about something, or the European Union lately worried about the possibility of conflict with Russia. in Ukraine, or you see the U.S. accusing China of having trade wars with China. So you see a lot of things in the news about how these countries seem to be disagreeing, or they hold different ideologies. And yet here, this is one project where they are all working together. And it's not a project where they are sending money to France and saying, please build this fusion machine. No, in fact, they are all sending parts. They're sending components. Money, yes, but money is only about 10% of their contribution. Most of the components, or most of their contributions, are as components. So why do these countries that do not always agree, why are they working so hard on this? Because they believe in a common cause of fusion power. So how can this be so important? Well, you've all learned, you've all just had your quiz, so you may know about some of this. Fusion is the most abundant source of energy in the universe. So you will hear about solar power and wind power, and you will hear about petroleum, where we put petrol in our buses and our cars and our motorbikes. Fusion is actually the source of much of that energy from a distance. The very last question of your quiz was, how far away is the sun? 150 million kilometers. So in the heart of the sun, and when you look at the sky, every star that you see, in the center of it is making fusion. So how does this work? What is fusion? Fusion is when you take two very light elements of two very light forms of hydrogen. Hydrogen is the lightest element, and you force them together. The two nuclei, each molecule each atom has a nucleus at its center, and you force those two elements of hydrogen together. That's a very, very unnatural thing. It requires a huge amount of force because each nucleus is positively charged, so they want to push against each other. But in the center of the sun is basically a big, big ball of hydrogen gas. And at the center of the sun, the density is so high. It is almost 70 times the density of steel. Even though it's hydrogen and it's a gas, it is super, super dense. Why? Because the sun is about 300,000 times the density of Earth. The weight, the volume, the size of Earth. And so the gravitational force at the center of the Earth, if we took you on a trip to the center of the Earth, it would be very devastating because the gravitational force is stronger the closer you get to the center of the Earth. And at the center of the sun, even 300,000 times stronger. So that is how the sun, at its very center, with gravitational force, it pushes these nuclei together. Almost 600 million tons per second of hydrogen is fusion energy. And in that reaction, the famous Einstein equation, E equals mc squared, energy is equal to mass times the speed of light squared. So what this really means is that a tiny amount of matter is converted to a large amount of energy. And from this, the sun shines. The sun continues to, as we see it, it continues to shine. It continues to burn. And this is where we get solar power. It's where we get light and life and even heat on Earth. So how is it possible to replicate, to build a sun on Earth? We do this through a machine that we call a tokamak. This idea was invented in the 1950s in Russia by a soldier, a Soviet soldier. At that time, it was the Soviet Union. He was stationed by himself on an island, and he had no big formal education, but he was trying to solve this puzzle. Because for about 100 years, all over the world, our scientists have known what I just showed you before that the source of life and heat on Earth is fusion. But here, for more than 50 years, scientists were asking, how can we harness this energy? So how do we do it? We take two forms of hydrogen called deuterium and tritium, and we create a reaction. This is the reaction we know, where these two forms of hydrogen create a helium nucleus and a neutron. So let's look at this in a little bit more detail. The orange balls here represent a proton, and normally, normal hydrogen that is all around us in the air just has one orange ball. That's all it's really got. That's a proton and an electron flying around it. So these gray balls normally are not part of hydrogen, but in seawater, in water, you can find this form of hydrogen. It still has all the same chemical properties, but it has an extra neutron, so it weighs about twice as much. This is called deuterium. This is naturally occurring. And this form of hydrogen with two neutrons now has 3 times the weight, and we call it tritium. So tritium is, there's lots of deuterium on Earth. These are the two fuels for fusion. Deuterium, we have enough because it's in seawater. We have enough to last us for millions of years of supply. But tritium, we only have maybe tens of thousands of grams of tritium. Tritium is not very much naturally occurring. We make it in some of the reactors, some of the fission reactors. And what we do in this tokamak is we breed the tritium. So another element on Earth that's very abundant is lithium. We use lithium in our phone batteries, for example, but lithium is very abundant in the core of the Earth. Again, millions of years of supply. So here, with just a little bit of deuterium and a little bit of tritium, we inject this as a gas into this donut-shaped vessel. It's a round vessel. And why do we call it a tokamak? Because this Soviet soldier came up with this idea, maybe we could do fusion like this, where we put gas into this machine and we heat it to a super, super, super hot temperature. So at the core of the sun, where we're making fusion, the core of the sun is about 15 million degrees, 15 million degrees. We're going to make a machine here that is 10 times hotter than the core of the sun, 150 million degrees. Sounds like science fiction, right? But we've already done it. So not here at ITER, but we've heated to this high already. So we put these two forms of hydrogen as a gas here into the machine. We heat it to a very high temperature. Why is that necessary? Because for particles like this, heat is equivalent to speed, to velocity. So the higher the temperature, the faster the particles move. If you run an electrical current through the gas, you split the nuclei from the electrons, so you form what we call a plasma. Normally, your teachers will tell you there are 3 states of matter: solid, liquid, gas. But there is a 4th state, and you've all seen it. Because when you see lightning in the sky, that's plasma. That is when a very high amount of electricity runs through the atmosphere, and it suddenly, for just a very short time, when you see lightning, that is converting the air to plasma. The same thing you see in a light bulb, in a fluorescent light bulb. There's gas inside that light bulb, and when you run electricity through it, it lights up. That's when it lights up, when you see the light bulb of a fluorescent light bulb, that's a plasma. Okay, so by running an electrical current through this gas, what happens is we create a circular field, magnetic field. And by making the nuclei separate from the electrons, it means that everything is positively charged. Why is that important? Because we have 150 million degrees, and there is no way that any material on Earth can withstand that temperature. Everything should melt. So what do? We create a magnetic cage, an invisible magnetic cage in this machine that is shaped, the shape of the magnetic cage is shaped just like this steel cage. So it holds, the magnets hold all of the charged particles. So you see that from this reaction, you get a helium nucleus and you get a neutron. And you may not know these units, but the incoming energy is 0.7 MeV, mega electron volts. And magically, the outcoming energy is, in this case, the helium nucleus, 5 times more. That is, again, an example of Einstein's equation, a tiny bit of matter converted to a lot of energy in fusion. So you make this, helium nucleus, which is 5 times more energetic, and then this neutron. This neutron is 20 times 14 divided by 0.7, 20 times more energetic. So that's where Einstein's famous equation is working. A little bit of matter gets converted to a lot of energy. What's important about that? What is important is that this neutron is the only uncharged particle that you see. So the magnetic cage will hold everything else, but not the neutron. The neutron escapes and it shoots into the wall here, into the metal wall. And just like if you were shooting with a gun, if you were shooting a bullet into a panel of steel, the bullet would transfer, it would stop by the steel. And if you felt the steel, it would be very, very hot where the bullet hit, because the kinetic energy of the bullet would transfer to thermal energy, to heat. So this neutron, if you released it in free space, it is so incredibly energetic, it would go from the Earth to the moon in about 8 or 9 seconds. That's how fast it is. So when it hits the wall, the steel wall, it transfers all of its kinetic energy into thermal energy, and behind the wall, you have water. So the energy of the neutrons hitting the wall converts to, heats the water converts to steam, and in a commercial plant, the steam will make electricity in a turbine. So that's how it works. Now you know everything that you need to know about how we're going to make a sun on Earth. Now, why? Why do we want to make it? What are the advantages? First of all, unlike solar and wind, you can run fusion power plants all the time. So it's baseload. India and Europe right now get a lot of their energy from petroleum plants, coal plants, fossil fuel plants, etc. But this is carbon free. So it can't be, it's not going to send, when we run coal plants or petroleum plants, they send their energy, their waste products, which is carbon and other greenhouse gases, into the air. And that's why we're getting climate change, because of all the waste products in the air. So this is carbon free. So that's very good. It's also abundant. I mentioned to you that there's plenty of fuel in seawater and in the lithium in the Earth's crust, and it's safe. So the nuclear power plants that are out there today use fission. So how is that different? With fission, you have a couple of 100 tons of uranium or plutonium, a very heavy molecule, in the fission plant, and that fission plant makes uses a different reaction. Instead of combining the nuclei, it splits the nuclei, and you split it with a neutron, and that splitting makes more neutrons. So you create a chain reaction, and if that chain reaction is not properly controlled, you can have a meltdown. So you have all lived through hearing about Fukushima, and you know that maybe in the 1980s, there was the Chernobyl accident. This is what happens when fission is not properly controlled, if there's a runaway. But with fusion, the reason we call it safe is because the physics are very, very different. In this machine, you only have, instead of several hundred tons of uranium, you only have 2 to 3 grams of deuterium and tritium. So if this machine has an accident, it just stops. There's no buildup of heat. You cannot explode it or discharge things across the atmosphere. So it's very, very safe. And economic, why is it economic? Well, it's very expensive to build,
Yes, yes, yes.
but the fuel is,
And it's India Today online and Financial Express online.
I think somebody has their microphone on.
Yeah, and it,
Thank you. Okay. So why is it economic? Because when you study history and the history of energy, ask yourself the question, how much have the countries of the world spent in, say, the last 100 years on conflicts, on wars, where they were trying to locate themselves close to petroleum resources? Because petroleum, for example, here in the Middle East, you have a lot of petroleum, yeah? So this is a place where you've had a lot of wars, where countries are trying to get access, position themselves to get access to that petroleum. So when you calculate the cost of those wars, or when you calculate that the petroleum is putting its waste into the atmosphere as we burn oil and coal, or we're causing sickness, pollution. At times, the streets of our big cities are almost uninhabitable because the pollution is so bad. Yeah, so those are all the costs we have to calculate with energy. And the fact that none of that happens with fusion means economically it's very safe. So I want to show you just a couple more things and then we'll get the tour started. But here's the sun and here's a tokamak. This is the sun on Earth. So ITER, this is a graphic of ITER's design. ITER is designed to make fusion at industrial scale. And we have one more unit I want to describe. It's just called Q. Q is what plasma physicists use to describe a ratio. How much power do you get out for how much power do you get in? We want to have a Q of 10. So what does that really mean? Well, first of all, you inject, I said like in a light bulb, you have gas. So you put the deuterium tritium gas in. You run a current, again like a light bulb, converts the gas to plasma and starts to heat it. Then you put in microwaves, electromagnetic waves, just like you might have a microwave at home or in a restaurant where you heat food. This is like having a very, very much stronger microwave, and you continue to heat it. And then you have high energy neutral particles, and in combination, you get to 150 million degrees, and you want to contain that. So we use 3 types of magnets. This magnet, you're going to start to see these components when I take you into the tour. These magnets in the center are built in modules. This is called the central solenoid. How big is this? Here's a man. Here's a human. Yeah, so you can see this magnet is super huge. It's being made in San Diego. And then these magnets, shown here in gold or brown, these D-shaped magnets are called toroidal because this is a torus and they're shaped around the torus. These are being made about half in Japan and half in Italy. Then we have round magnets, ring-shaped magnets. This is a cutaway, but this magnet, if you saw it all, it would be shaped like a ring. This one was made in China. This one on the top here is almost finished. It's being made in Russia. And these are too big to ship. So this magnet is about 10 meters in diameter. This magnet is about 10 meters in diameter. So we can actually ship these, build them somewhere else, ship them here. But these are too big. This one, I'm going to show you on our tour, this actual magnet. It's finished now. And this magnet was made here. It's about 17 meters in diameter. So too big for the roadway. Even with this magnet, when it was shipped, the French authorities had to carve away part of the roadway. They were using heavy material to cut away at the mountainside so that they could make the way a bit bigger so we could get this magnet to come up the road, right? But with these 3 types of magnets, central solenoid, toroidal field coils, and poloidal field coils, all magnets, superconducting magnets, we'll explain superconduction. These magnets are what create what I told you before was this invisible magnetic cage inside the metal cage, inside the metal walls of the tokamak. Yeah? So, we've been making these for years. India has its own small tokamaks that are experimental at university level. Many countries have them. This one is in the UK. This is the largest one we made to date. The largest one ever made. And you see this fellow. So pay attention to his size because I'm going to show you, this is called JET, Joint European Torus. Now, let's look at the next one and what you see. This was what you just saw, JET. Okay, so here we have Joint European Torus, and here you have ITER. Yeah, looks a lot bigger. But what's the difference? This comes back to Q. What I said, Q is the ratio of power coming out versus power coming in. So Q is influenced by three things: plasma density, which we can't change, magnetic field strength, how strong are your magnets, and plasma volume. So with the magnets that you just saw, the magnets that we're making using an ITER, we need, for a Q that we want to have of 10, we need a volume this size, right? So this is JET. There was 23 megawatts of heating in JET for and only got 16 megawatts out. Well, that's good, but it's not very practical because if you're using more energy putting in than you're getting out, that's not a very useful machine. So in order to demonstrate feasibility, we had to make an industrial-sized machine with all these countries making partnerships, and now we can put 50 megawatts of heating in, and we get 500 megawatts out. That's where you get 10. 10 times the power out from the power in. And to do that, we went from a volume of 80 cubic meters to a volume of 830 cubic meters. And then we're building this machine with contributions from all these different countries. And the biggest component, which is this, you see this big cage that holds it all? This giant component, 30 meters in diameter, 30 meters high. Guess where this is made? In Hazira, in India. In India, there's a giant factory that's one of the few factories in the world that is capable of making these steel parts, which can be sent to Europe because this is too big to ship. So it's all sent in pieces from India with ships to Europe. And I will show you, I showed you that Indian building. I'll show you inside that building where Indian supervisors are supervising German welders under French nuclear regulation in an international site to make this cage that is the overall, so the vacuum vessel is this. This vessel is called the cryostat. The cryostat is like a gigantic thermos that holds this entire machine in a controlled, beautiful, light vacuum, very cool environment and allows this whole thing to work. So India is sort of the mother of the machine, the one that holds this whole machine together. The project was born in November 1985, so it sounds very old. This is Ronald Reagan, who was the American president, and Mikhail Gorbachev, who was the secretary of the Soviet Union at the time. They had nuclear weapons, and they were trying to meet as enemies to become friends and trying to reduce the number of nuclear bombs that each country had. They decided they wanted to do something positive. By this time, the idea of the tokamak was well known, and they decided that their country would ask other countries to join to build a machine that they would call ITER. This is where the project was born. And here, in 2006, leaders from all of these countries that I have named got together. So this is Jacques Chirac. He was the president of France at the time. And here you see a very important fellow. His name is Anil Kakodkar. Anil Kakodkar was the father of much of the Indian nuclear program. And he was coming to France, to the Elysee Palace in Paris, where this agreement, along with a Russian, an American, a Chinese, a Japanese, a Korean, and other Europeans, were all joining here to sign the ITER agreement. And this is India becoming part of it. So in August, a few years later, it became a flat field, a platform, and this is where you see it today, where we're going to take our tour. So in this simplified drawing, you can see that India is creating the giant piece that goes around everything. India is actually, this is a simplified drawing. India is also creating, for example, all of these panels here are coming from India. So the vacuum vessel itself is being made in Korea and Europe with some parts by Russia, but India is then putting creating all of these steel, very, very precisely formed tiles that make up the first wall of the vacuum vessel. And then various countries are making magnets or making the feeders that bring in the electricity and the helium to cool and so forth. So ITER is about 75% done. We've been working right through COVID. About a year ago, we had a celebration to start the assembly phase, and it was virtual here in this big hall. Emmanuel Macron was the host, the French president. We also had a statement from Narendra Modi from India, and from Vladimir Putin of Russia, from Moon Jae-in of Korea, Xi Jinping of China, and so forth. So all of these countries, again, repledging that despite any differences they have, they're going to work together on ITER. So there's been this manufacturing going on. This is after a bunch of parts were shipped for the cryostat, that big thermos I told you about. This is an old photograph from about 10 months ago, when they had all arrived in the tokamak, in the ITER site. And I'm going to show you in the tour how they're now almost finished putting all of these pieces together. So parts being made all over the world that are being shipped from Marseille up this itinerary that I showed you to the ITER facility. So let's go now inside to the tour. As we go to...
Can I just interrupt for a second with your permission, sir?
Please.
So there are some questions in young minds, which is there in chat box. So if you just clarify those discussion or question, whatever, then they will definitely going to enjoy more. So over to you, Soumya. Will you please switch on your video and ask questions? It's written in chat box.
Okay, I'm going to try to come back to you here and do that. Good. So let's go to the chat box. Here we go.
Okay, so we have this question from Aryan Bardeja, grade 9th.
Okay.
In Shiv Nadar School, Noida.
Okay. Okay, so it's a very, very good question. And the answer is that the best materials that we have on Earth that can try to hold something this hot are not even close to being able to contain it, because the materials will be able to withstand maybe up to 5,000 or 6,000 degrees, and we want to contain a plasma of 150 million degrees. So it sounds very impossible. So instead of holding it together with a material, we hold it together, or how we are doing it is with this magnetic cage, right? So in fact, we ensure that this very, very hot sun-like material, if you went to the sun, if we traveled to the sun, we would find that all of that, because it's a plasma, all of that material is charged, right? So it has a positive charge or a negative charge. That means that magnets will contain it. So you could contain the sun not with a physical material, but with a magnetic cage. And that's how we're containing it here, with a magnetic cage. The only thing that escapes the magnetic cage, is the neutron, because the neutron has no charge. So this is what we want, because we contain everything that's super hot except the neutron. The neutron escapes, and the neutron hits the steel and heats it, but it heats it at a manageable temperature. Next question.
Thank you, sir. So we have another question. What will be the amount of CO2 released during the fabrication of the fusion facilities compared to conventional power sectors?
Sure, that's a very good question, because if we had a perfect, well, you hear discussions about climate change and the need for carbon-free energy. But in fact, every time that we manufacture solar cells, every time that we manufacture wind turbines, in order to get green energy, the manufacturing process itself is creating a carbon release. In fact, you may know many of the factories that are making I would say, certainly not all, but a lot of the factories, a very large percentage of the factories that are making solar panels today are in China. And China is using, people don't talk about this much in the news, but China is using coal-generated electricity, coal-fired electrical plants, to use the electricity that they're using to make the panels. So it's kind of counterproductive, because you're putting carbon into the air. So I don't know exactly. I can't give you the exact amount of carbon that's being generated, but it's certainly inefficient, because you saw, and you will see more, a lot of concrete that is making the buildings, and a lot of steel. And right now, as humans, we're just, well, I would say we still don't quite, we know how, but we don't know how to manufacture steel or concrete without using petroleum. So what do I mean? We know how, but we don't know how. We found processes where you can make petroleum, you can make concrete, and you can make steel without using petroleum, but we haven't really scaled them up. We can do it at small scale. We know how to do it, but we haven't scaled it up. So if we had a perfect fusion plant built today, and we don't, we're working on it, but if we had a perfect plant today, and we wanted to replace all the coal plants in the world, all the fossil fuel plants, natural gas plants, etc., we wanted to replace that all with fusion plants, it would not be a smart idea yet, because we would be making a lot of concrete and steel using petroleum. So in the fabrication process, as this student has very correctly noted, in the fabrication process, you would be releasing carbon. So we need multiple technologies, including how to make concrete and steel in a better way. Now, what we are seeing, some of you will know about 3D printing, right? So 3D printing mostly we use with plastics, but we can now 3D print with metals, and there are new 3D printing techniques. For example, the company Rolls-Royce is using 3D printing of metals that will actually make stronger metal parts for aircraft engines than what they are using making steel processes. So with 3D printing, this is, if we get to the point of being able to fabricate in multiple metals with 3D printing, that would be a way that you could reduce the carbon footprint of the manufacturing process, of the fabrication process. So next question.
Thank you, sir. So the next question is from Shrihan Mathur of grade 8 Shiv Nadar School. How will we contain the replicated sun? It can eventually collapse due to intense pressure. The core can collapse.
Yeah. So actually, it's sort of true in the sense that it's very, very unstable. So it's not dangerous because if you think of when people think about nuclear, they either think of nuclear bombs or they think of nuclear fission and the safety issues with a meltdown. Yeah. So in a fission reaction, this is not ITER, this is not fusion, not the sun, but in a fission reactor, as I mentioned, you have a huge amount of uranium or plutonium, something very heavy, and a chain reaction. So that chain reaction means you send a neutron, you split the nucleus, that creates waste. You split the next, and more neutrons that split more nuclei. So you have a chain reaction, and this builds up a huge amount of heat. So if you have a problem with containing, and you don't have a lot, you say that you're cooling that with pumps running water through it. That's really what happens in a fission reactor. If you lose electricity for those pumps and the pumps stop, you have a big problem, and it can collapse because you have all this heat, and you can just melt the core, and you create a Chernobyl or a Fukushima. In fusion, the big thing to remember from what I told you is that we only have 2 to 3 grams. So 2 to 3 grams is just, it's like the weight of this paperclip. It's a tiny, tiny amount. Now it's spread over 830 cubic meters. It's a huge cage, but it's a very, very tiny amount of material. So the question is correct in the sense that it's very easy to collapse it because any disruption will just stop the reaction. But what is not, it's not dangerous because there's this very tiny amount of material, and you go literally from 150 million degrees to 0 like that, very, very quickly. There's no damage that occurs from stopping the reaction. What's difficult is to make the reaction continue. So when I mentioned that JET had this 23 megawatts of heating in and 16 megawatts out, which wasn't good enough even to break even. But that was only for a microsecond. Recently, about 2 weeks ago, this is not public yet. I can tell you it's information they have not shared publicly. But the scientists at JET told me that they did 10 megawatts for about 5 seconds. Well, 10 megawatts is enough to put you on the edge of industrial scale, and 5 seconds for that amount is a world record. That's never been done before. In China, there is a tokamak smaller than ITER called EAST, and at EAST, Chinese scientists have maintained nothing that high, but they've maintained for about 100 seconds, right? So that means that it's a pulse. It's not a pulse like this, but it's a pulse like this. 100 seconds is a minute and 40 seconds. So you kept their amount for a while, and then it goes down again. So with ITER, when I say we want 500 megawatts, that is for 400 seconds, for 6 minutes. So if you look at the pulse, it will be like this, spread out. And as you lengthen these pulses, you get to a near steady state, so you can produce that heating. So would the core collapse? Sure. If you just stopped putting fuel in, it collapses. If you stopped heating, it collapses. But it doesn't collapse in a dangerous way. It just stops. Next question.
So we have next question from Aryan Vardeja of grade 9, Shiv Nadar School, Noida. So the question is, how will we produce electricity through generating plasma?
Good. So if you look at how do we generate electricity with coal today? Yeah. There are several ways that you can do it, but the most common way is that you burn the coal, and the coal makes a lot of heat. But heat isn't electricity. So what do you do with it? You have what we call a heat exchanger. So the coal could burn, well, let me give you a different example. In your home, uh, some of you might have coal or oil as heating, right? So it makes heat, but what do you actually do with that heat? You heat a boiler. So inside the boiler, you have a bunch of water, right? And you're burning the coal or the oil in a way that goes through very hot oil through tubes inside this, and it heats the water. And then the water goes through your house, and you have radiators, right? If you've ever seen radiators that will have the hot water going from there. So if you get that water hot enough in an oil plant or a coal plant, that water turns to steam, and the steam can drive a turbine. So you run this turbine with hot steam, and from that turbine, you use the spinning turbine to then create electricity through a generator, right? So it is much like you do in a car. You have electricity in your car. It doesn't all come from the battery. It comes also from the generator in your car. So you burn petrol. You put it in the tank. It turns the motor. The motor has a generator. The generator makes electricity. So in the plasma, you heat it to a very hot temperature, and that temperature, the neutrons hit the walls. The walls become very, very hot, not 150 million degrees, but it receives the neutrons, and behind the walls, you have water. And that water gets collected, and it goes to the cooling system, which also, by the way, India is building here. And in that cooling system, we remove the heat. In a commercial plant, in that cooling system, the way that you cool is by running a steam generator and generating electricity. I hope that's clear. Next question.
Thank you, sir. So the next question is from Soumya Mittal. She wants to know if it's possible to use the released helium, which can improve the efficiency of the reactor.
That's a super smart question. I think that in general, well, you may know this, helium used to be something that was considered very plentiful. We have a lot of helium still, but we've used so much helium because it's used in a lot of research. And we've used so much helium that now some countries talk about helium reserves. We used to, when I was a kid, we would have a lot of helium balloons, right? Where you would have a tank of helium, you blow up balloons, and it was fun because you could let the helium go, and it would go into, the balloons were lighter than air, so they would fly into the atmosphere. But helium can also be used in turbines that are more efficient than steam turbines. So steam turbines generally about the most efficient are 35 or 40%. That means you lose 60 or 65% of the energy. So it's not very efficient, but it's the best that we have. Helium turbines can get you up to 60 or 65%. In answer to the question, right now, the answer is no. We don't plan to use the helium that way. Why? Because the amount is so small. You only have 2 to 3 grams of fuel. So as you're making helium, the amount of helium that you're generating is so small that it's not enough as volume that we could actually use it as a more efficient way of driving the turbine. But people are considering that. It's a very good question.
Thank you so much, sir. We are over with the questions.
Okay.
I just want to take 1 minute or maybe 30 seconds. There are many very good discussion going on. So what we are going to do, we will copy all this and will post to you. During your session, children are discussing among themselves, and we are taking those things from YouTube and posting here. So it will give us just 1 day. We will post everything to you. You will be so happy.
Okay, good.
Have ignited so many young minds.
I want to say one more thing about helium before we move on, because there's another part of the helium question that I didn't cover too much in there. I'll see how good your memory is. You remember the diagram that we had, which is of this where you saw the reaction, where you saw the incoming deuterium, tritium, and a flash, and then the outcoming helium and neutron. That helium coming out is about 5 times more energetic than the particles coming in. So yes, in answer to what I think Samya Mittal was asking, in answer to that question, that helium, because it's more energetic, it continues to fly around along with all the other particles because it's charged, and it continues to transfer its energy to the deuterium and tritium. So it's actually heating, meaning using its increased energy to keep the velocity, the heat, the speed up. So it is a form of self-heating. And actually, one of the things that happens in the core of the sun is what we call a burning plasma. A burning plasma means that you don't have to inject external heating. You just have, the plasma is largely self-heating. So obviously, I told you about the 3 heating systems, but how does the sun work? The sun doesn't have an electrical generator sending, helping to make the fusion reaction. It is doing its own burning plasma. We've never had that on Earth. All the tokamaks that have been made, there have been hundreds of tokamaks made at small scale, up to jet, which I showed you. But none of them have been big enough so that scientists could study a burning plasma. So yes, this helium coming from the reaction, as long as it's still energetic, it continues to heat. So when we get more than 50% of the heating coming from the helium, from the fusion reaction itself, that's what we call a burning or largely self-heating plasma. So yes, I want to, and that once the helium gets fully depleted and it wears out its energy, it falls to the bottom of the tokamak, and we collect it and remove it. Yeah. So that's just one more point about the helium. Now, I should say this before we go to the tour. You had a video that you were considering to show me. Would you like to show the video now? If I remember right, there was a video, or should we wait on that?
Sir, we have one more question to go. After that, we will play the video.
Okay, go ahead.
So, one more question from Angad Singh. Why do we need the nuclear reactor if its ultimate purpose is to heat water and turn the turbines? We can heat water to a very high temperature and turn the turbines?
Okay, because how would you heat that water? The way that we heat water today is either by, you could heat water with a solar panel. You could heat water with boiling it on the stove, but you need to get that heat from something. So if you are getting that heat, for example, by burning wood or by burning coal or by burning oil, then you have a waste product. Because as you are burning it, there are gases coming off of that. And those gases, the waste products, are carbon and other greenhouse gases. They go, like methane, for example, they go into the atmosphere and they are destroying our planet. So the cost of that may not seem evident at the time, but the cost is very, very high. It's hurting our own environment by putting this carbon, this form of heating water, into the atmosphere. So we need something carbon-free. So with solar panels, you could use that to heat water, but the problem is that if you use the solar panels to heat water, you are actually using fusion energy because the sun at a distance is making fusion energy and heating. But that heating that you're getting is very, very, it's at this distance of, you remember from the quiz, 150 million kilometers. So that at that distance, it's very inefficient. So if I want to power a city, even a relatively small city like, say, Hazira or Maharashtra or Maharashtra province Ahmedabad, that's not so small. If you get to something like Mumbai or Delhi and you want to produce all of your energy for that city, all of your electricity, the batteries to run clean cars, etc. You want to run all your lifestyle from electricity, and you want to do that with solar and wind. You have a huge problem because you will be covering up so much land mass with all of that solar and wind panels. Not only to mention that the solar and wind will only work when the sun is shining or when the wind is blowing, but you're covering so much area that you are destroying a huge habitat of the plants and animals and farmland and so forth. So it's kind of counterproductive because you're using fusion energy for your solar panels, but at a great distance. So why do we want to use fusion? Is because and why do we reproduce the sun on Earth? Is because it's very concentrated. It's relatively small plant, very powerful, very clean, not putting your waste into the atmosphere. That's why. So would you like to show the video?
Sir, looking at the time, I think we should proceed for virtual visit because it will take at least 40 to 45 minutes. Also, sir, at the end of your session, grade 11 has composed a kind of theater or act just to pay tribute to you. So that we will showing after the virtual visit. And
okay.
Over to you, sir.
Okay, so I will go back to, let's see. So I've stopped sharing. I'm going to open sharing again. And you should all see, we're back to the virtual visit, right? You can all see? Okay. So I've been showing you these aerial views. We're going to go now to this end of the site. So the site overall is about 1 kilometer long and about 400 meters wide. We're going to start on this end where we have the electrical switchyard. So I'm sitting here in this building. These are contractor buildings, more staff and contractor buildings. But this part is the factories and the support systems, and the tokamak itself is in here. Not finished, we're assembling it. So we'll go to the electrical switchyard. So when we see this now from this area of the work site, one of the things I want to mention as we go along in our tour is the degree of where things come from. So here, this may not seem very remarkable. Many of you may have seen a switchyard as you drive by it, maybe not close up, but you have things like these transformers here, right? So these transformers, these are, much of the equipment here is made in America. It's made in the US and shipped to ITER to make the electricity that powers the facility. So this electrical switchyard is not remarkable. It's not unusual. It's big. It would be big enough for a small city. But this is why you are listening to me now, because my computer is getting its power from this switchyard. But still, it's just incoming AC, alternating current power supply. We have a second switchyard, however, which is over here. Now it looks like it's the same, but actually the components are very, very different. So in this switchyard, you will see strange looking thyristors and alternators and generators. Much of this is coming from China. There's about 1 hectare of equipment that is being installed here, which is all designed to take the incoming AC power and store it up. Now, why do we store it up? I don't know if you know the term capacitor, but a capacitor is an electrical component much simpler than this, where you can put in electricity and it stores it up. It's kind of like a battery, but different. It doesn't work like a battery. It just manages to store the electricity up, and then you can release it in a very quick shot. And by releasing it and storing it and releasing it, you have an advantage that you could put a very high electricity pulse in without actually creating a big energy loss on the grid. So why is that important? Because in this part of the electrical grid, we are sharing this with all of our neighbors who live in the cities all around us. So if we try to take a sudden giant amount of energy from the electrical grid through this system, we can suddenly turn off everybody's electricity in the neighboring cities. So that would not win us very many friends. So this system, the reason it's important is because this second switch yard, storing up all of this electricity, can then deliver it in a microsecond pulse to the magnets in order to start the machine. It's like the starter on a car, turning the key. That's what this is. It's like a you know, being able to create the spark for it. Now, why is all of that even important? Because when we go back to the next buildings we're going to go into, here's the switch yard. These buildings are what we call magnet power conversion buildings. Why are they important? Well, Eater's magnets are electromagnets. So what does that mean? It means that if I actually touch the, if you see on my magnet right now, you can see if I hold up some other piece of metal, it doesn't stick. There's no magnetism here. It's not a magnet until I power it with electricity. So it's only working as an electromagnet. So if we go inside these buildings next, you'll see a lot of electrical equipment also in these exterior bays. So let's do it. Here you have these two buildings, magnet power conversion buildings, and outside in the electrical bays is equipment coming from India and Korea and China and Russia. If we go inside the buildings, we see again a ton of different pieces of electrical equipment. So I am not smart enough to tell you what every single piece does, but for example, these long yellow metal pieces are really like extension cords. Really, I know that sounds funny, but they're like giant extension cords where the Russians have manufactured all of these yellow, what we call bus bars. And why? Because we are taking the current, the AC current, the alternating current coming in, and we're changing it, converting it through many pieces of equipment to DC current. Some of it is still here wrapped up. We haven't hooked it up yet. This DC current then will run along these yellow bus bars at exactly the right voltage and amperage to power the electrical magnets, right? To power the Eater's huge magnets. And so during COVID, Russia was sending, most countries are not connected to Europe, but most of Eater's countries are not connected to Europe by land. They're shipping their components, like India, through the water, in some cases by airplane, but most of them are too big. They come over ships. But Russia was shipping these kinds of things via land, giant trucks through the middle of the pandemic, bringing all of this equipment to be actually installed at the Eater worksite. Yeah, so that's the one characteristic of the magnets, that they have to be powered to be electromagnets. The second characteristic is that they have to be cooled. Why? Because this material that I showed you, when I showed you this little bit of magnet, this material is called niobium tin, and niobium titanium. What we need for these magnets to be powerful enough to contain the sun, to contain ITER's little sun, is they have to be superconducting. So some of you may be advanced enough in your classes that you have seen equations where they have a little signal of the omega. It's a symbol that is showing resistance. Now, in most materials, electrical flow can be stopped or slowed down, right? So if I put electricity in water when you're in the bathtub, that's a very bad idea because water conducts electricity very much. But even water is not superconductive. If you stick your fingers into the wall socket, I hope all of your parents have trained you not to do that, but if you stick your fingers in the wall socket, you will get shocked because you have copper wire in there that is conducting. But even that copper wire is not superconducting. There's some resistance. And if you cover your hands in gloves and you put them into the wall socket, you would not get shocked. Why? Because the gloves don't conduct electricity. There the resistance is very, very high. So with ITER's magnets, we have to get them to superconducting, which means that the flow of electrons is completely free. Resistance is zero. So much, much better even than the water in your bathtub or sticking your fingers into the wall socket with copper. ITER superconducting magnets, niobium tin, niobium titanium, take the resistance to completely zero. That's how we get the magnets to be so unbelievably strong that they can hold in the sun. But how do we do that? It's not really very easy because niobium tin and niobium titanium can only be superconducting if they are cooled down to an incredibly cold temperature, minus 269 degrees. How can you cool something to that cool? In your physics class, you might have heard about absolute zero. Absolute zero is the temperature at which all motion stops. Even the molecules and atoms and so forth completely stop moving. So we don't have to get this temperature down to absolute zero, which would be minus 273 degrees. That's absolute zero. That's in Celsius or centigrade, but we can also use a unit called Kelvin. Kelvin is very much like centigrade. It's another way of calling it, but 0 degrees Kelvin is equal to minus 273 degrees, and that is where you get to absolute zero. So minus 269 degrees Celsius is 4 degrees Kelvin. That is the operating temperature for these magnets. Only 4 degrees above absolute zero. How is it possible to do that? Well, the answer is here. This is the cryogenics plant. Cryogenics is what flows through the middle. Remember I showed you the hole in the middle of this wire, this superconducting wire. We do this with these giant tanks of liquid helium. So liquid helium can get you down to minus 269 degrees. There's also some liquid nitrogen, but it doesn't get that cold. We use the liquid nitrogen for some other things, and the liquid helium here for cooling the magnets. So remember, we had the magnet conversion buildings here that are putting the right electricity to the magnets, but here we're going to have the cryogenics plant which cools them. So we go inside the cryogenics plant next, and what you will see in the cryogenics plant looks a little bit like if you open the back of your refrigerator. I would not recommend doing that unless you're a very curious scientist. But in the back of your refrigerator, you're going to see a bunch of pipes, some little tanks, much smaller than this, of course, and some compressors. And what are all these doing? Well, helium, as you know, is naturally a gas. And this is compressing the helium, putting it under intense pressure, and doing that so that you can essentially cool the helium down to minus 269 degrees. And we will have at ITER 25 metric tons of liquid helium. Well, helium is, as we said earlier, in limited supply. We can't lose it. So this system has to be really super airtight. To do this, it's a combination of partnership between France, a few other European countries, and India. So India is providing a lot of these cryolines. The cryolines, we have kilometers of cryolines that are coming from, cryolines are the cryogenic piping lines, or piping. So we refer to them as cryolines, but it's just piping. That is what is taking this liquid helium and delivering it to the across the way to the tokamak. And right now, if you look at the facility, you can see that when you come from the cryogenics plant, you got to get it somehow out of here over to here, because it's got to go in here and into the tokamak. We are in the process of building a bridge now. It's not started yet, you don't see anything, but there will be an overhead bridge that connects these two buildings so that the cryogenics cooled to minus 269 degrees, this liquid helium can come in here, and eventually go into that little hole that I showed you in the center of the magnet, so that the magnets can be cooled to minus 269 degrees. So think about the engineering. In the center of the plasma, you have 150 million degrees, the hottest point in the universe. And just a few meters away, in the magnets that are creating this magnetic cage, strong enough and tight enough to hold the plasma away from the walls, hold a 150 million degrees plasma, and in the core of those magnets, the temperature cooled through the cryogenic lines is minus 269 degrees. So the engineering involved in ITER is just really absolutely stunning. I want to take you now to another Indian contribution, which is this heat rejection system. So in a commercial facility, ITER will not produce electricity. ITER is an experimental plant. Normally, some of you were asking the question, how do you make electricity? Well, it's with the heat. You heat the plasma, and here normally you would have an electrical generator, a steam generator. This is where you would have the turbine and you would drive this. So ITER, because it's experimental, the scientists from all over the world, from India and China and Russia and Europe and Japan and the United States and so forth, will all be here studying everything that they can manage to study about this. And in fact, this building, which I won't take you on a tour, there's not much to see really, but this building is the diagnostics building. We will fill an entire 5-story building with instruments that measure not just things like temperature or pressure, but measure neutron flux. They measure just really thousands of parameters. So this, much more than you would do in a commercial machine. Why? Because the scientists want to study everything possible about this machine and its burning plasma so that they can optimize how to build the machines that follow. So it would be very impractical to have a steam generator for ITER. You could make electricity with ITER, but if you're constantly just going to be doing pulsing and taking it up and taking it down and doing various experiments, it's not very practical. So for the ITER machine, instead of a steam generator, we just have a giant heat exchanger where the heat coming from the machine will be eventually run through all of these pipes. And what do I mean by a heat exchanger? Well, inside this machine, you will have a cooling water system So it's a giant cooling basin. This doesn't look very sophisticated. It looks like somebody flooded it, but actually this is a quite finely tuned body of water that, combined with these giant, let me show you again this way, combined with these heat exchanger devices, all of these pipes taking out the heat, and then with the actual fans on the top. So these fans are at the top of a giant pump. And all of these fans and pumps and many of these lines are actually manufactured by India or by Europe. So India sent us these things in pieces, and then an Italian company with Indian supervision is putting together these pumps and these big ventilators. And this is all designed to just remove the heat, because if we don't remove the heat, then obviously we have a problem. So from the tokamak, underground, it comes, the heat comes out from the tokamak, 500 megawatts, but actually that's the design. We can go up to a much higher, really up to 750. And this part of the machine, this support system, is designed to remove 1,200 megawatts. So it has even greater capacity in case we need it to remove the heat from the machine. All right? So now I want to take you inside some factories. So we're going to, let's see, we're going to go inside this building. I told you that there's an Indian factory and a European factory. We'll first go into the European factory, which is where we make the magnets. Now, most of the magnets are made in factories all over the world, but remember I said that there were some that were just too big to ship, right? Well, this is an example of why they're too big to ship. So, here we have a magnet that is a ring-shaped magnet that is about 17 meters in diameter, and it's in the process of being made. How do we make this magnet? So I showed you with my hands what was a little slice of the magnet, right? This is what that wire looks like. So I showed you just a slice, like 1 centimeter, but this is a full amount of that magnet. And even though you saw how big it was, we are able to bend it. But of course we can't bend it by hand. We bend it with some of these machines. So it arrives, if you see this right here, this is how it arrives. It arrives in a big coil of this is, I would say, wire, but it's actually really, really, really strong steel. And that steel is then coming along here where we make it straight. We take it out of this curve and use machines to bend it and make it straight. And then we wrap it in insulation so that by the time it comes out, it actually looks white because we've wrapped it in insulation. And then it gets laid down here, and it's curved now into the precise shape that will create a 17-meter magnet. And you see over here, there's another coil. Here's another coil of incoming magnet, straightened, goes along here, and this one is shaped here. And so what we're doing here is putting magnets, laying this coil down in 2 strips. One from here along here, and the other one from this coil along here. So we're making double lines laying down into this circle. And we're laying it very tightly side by side, this insulated material. And then we go to the next stage. So in the next stage, we have multiple pieces of this magnet laid on top of each other, and we're connecting the ends of it together. So the little hole in the middle, remember I showed you that there's the hole in the middle of the cross section. We have to make sure that all those holes are perfectly connected because we're going to go layer by layer by layer of this magnet on top of itself. And then we go to the next stage. So I got to take you across to that. So here you can see what I just showed you. And here's the next stage as we start to put these magnets together until we actually have a stack. Now this is a magnet that's almost complete. So now we've laid the magnets together, and then we inject resin, and that resin helps to fill in the air gaps. So on this platform, we can actually tilt the magnet sideways. So we release all the air bubbles, and then we cover it with these various gaps, metal bands here, because niobium tin, niobium titanium is very fragile. And part of this process is just containing it all, because we want to have a very stable ring magnet now. This one is largely completed. The one that you saw on the other side of the facility is still being made, obviously. Yeah, but here is one that we've largely completed. So we're going to be able to take it out of the end of this building so it can be put in the tokamak. But first, before we put it in the tokamak, we have to, and now we're taking you can see inside the magnet. Now we're standing really on the inside. So you can see with a person how big this magnet really is. This whole thing is just a magnet that's going to be one out of many magnets that are used for this machine. You also see this piece here. What is this? This is the bottom half of a sort of cocoon. And the top half is sitting around here somewhere. I don't know. But in any case, you will take this magnet and lay it inside here and put a top half on it so that it looks like a worm, like a circular round worm. And why? Because here we can put in cryogenic helium and we can test the magnet, because we want to make sure we made it right. So we want to make sure that this thing will be superconducting before we take it out of the building. With this crane, we take it out of the building and across to the assembly hall. So this is where we're manufacturing that aspect. Then we also have the cryostat. So in the cryostat workshop, this is the building that was built for India. India owns this building. And before we go inside, I want you to look at this. This is something India has made. I'm going to tell you about it in a moment, but you can't really see it very well because it's covered up with insulation. This is called the upper cylinder. Just remember that name, upper cylinder. We'll talk about it a little bit more. But inside this building, all of the parts that India shipped from Hazira are being put together into, remember I showed you the photograph before where there were a bunch of kind of triangular shaped pieces? Here, the Indian welders the Indian supervisors are watching the German welders trying to make this into a lid, into the top piece of the overall cryostat. So if we go top down, we can see the welders working on this. And you see here, you see these lines? The pieces from Hazira were made at this size and then shipped. And here you see them being fitted together and welded so that we turn this whole thing into a lid. It's not done yet, but the lid will fit on top of the entire etcher machine. So to see a bit more of it now, we're going to go inside the assembly hall. So what is the assembly hall? On the work site, I've shown you a lot of these buildings. Here is where now we're actually kind of standing and looking at it. This is where this big fan on top of the heat exchanger was. Remember I showed you the heat exchanger? So now we're standing right there so we can get a good look at the assembly hall. So here's the tokamak building and here's the assembly hall. We're going to go inside the assembly hall. So from the Indian workshop, all of these pieces come in the back of the assembly hall. And here in the assembly hall, as we enter, you will see that one of the magnets has actually arrived. It's not installed yet, but it's arrived. So the assembly hall is connected to the tokamak building, where we'll go next. But before we go there, look at how they're connected, because this is showing you how we actually fit the machine together. You see these overhead cranes? They're very powerful. There are you see four. There's 1, 2, 3, 4. They're actually working in pairs. So this two pieces in a pair can hold 750 tons, and these two pieces in a pair can hold 750 tons. So combined, they can hold 1,500 tons, a very heavy component, pick it up from the floor, carry it over here along this track and I can't show you yet, but they will go inside the tokamak and lower it into the tokamak pit. So that's how assembly is conducted. But many parts have to be what we call pre-assembled. So the magnet that you saw in the assembly hall has been transported. One like it has been transported here to the assembly hall, so the magnet here can be picked up very, very carefully by the overhead crane, carried across and put in. But some components, it's not so easy. So this one, for example, is a piece of the vacuum vessel sector, the vacuum vessel. So the vacuum vessel is the inner part. This was the tokamak itself. And we can't just make the whole donut, the whole tokamak, and assemble it. It's way too heavy. So we take 360 degrees of the circle, and we do 40 degrees at a time. So this is 1/9, 40 out of 360. So this is 1/9 of the vacuum vessel sector. What you're going to do here is pick it up with the crane and place it in this tool. This is just a tool where you strap it in here, so it's very, very, very secure. Then the overhead cranes pick up the entire tool and flip it, so it moves 90 degrees, and then they put it into one of these big machines. There are two of these. These are called subsector assembly tools. Now that sounds very complicated. They're tall. It's about the height of an 8-story building, and you put this piece right in the middle. So you can't see it very easily, but I'll show you a different picture in a moment. If we go in there, there's one of these pieces, one of these vacuum vessel sectors sitting here in the middle of this piece. Why do you do that? Because we have to, before we put it into the tokamak pit, first we have to add 2 of those D-shaped magnets, and we have to add something else that's called a thermal shield. So how do we do that? We essentially we hold this vacuum vessel sector right here. Now you can see where the vacuum vessel sector is being held in the middle of one of these tools, in the belly. So let's zoom in a little bit. This is the vacuum vessel sector. It's a double-walled piece of the tokamak, of the wall. But remember, I said it's going to be 150 million degree plasma in here, but then we're going to join this D-shaped magnet here, made in Japan. This is going to be joined to the vacuum vessel sector, and in the middle of this magnet, we're going to put liquid helium to make it minus 269 degrees. So most of that engineering is done with the magnets themselves, the magnetic cage. But we also add, you see this very shiny piece of metal? This is actually coated in pure silver. It's a very thin sheet that is added on the outside of the vacuum vessel. This is made in Korea. And so here you have the vacuum vessel sector made either in Korea or Italy, and then a piece of thermal shield, and then a magnet here made in Japan or in Italy. And all of these pieces are put together using these giant tools. How is it possible to do that? Well, at the bottom, they have circular tracks. So the circular tracks are used to move the arms of this machine, this tool. So we move very, very, very slowly. We move this magnet inward until it can match up here and then be welded together. So this magnet weighs about 360 tons. That's about the weight of a 747 jetliner, an airplane. So you have a 747 jetliner, you have this, you put this all together, it's going to be about 1,100 tons. So can the cranes carry it? Yes, because each crane can carry 750 tons. Put them together, they can carry 1,500 tons. So that's how we managed to take these gigantic pieces and move them, these big pieces like this, connect them with the magnets, and move them into the overall tokamak machine. on the other side. So now we go to the final stop on our virtual tour into the actual tokamak building. Et voila! Here you have the heart of the actual machine, still being constructed. I know it doesn't look much like a tokamak, but I promise you we're going to get there. Right now, you just see this big circle of concrete and steel. So in the overhead, you see the cranes. This is where we just came from. So this is the assembly hall where we just were. And I said this crane track runs along, so you can bring these pieces in and very, very carefully, you position them all the way here in the bottom. Now, last summer, when everybody was celebrating, what were they celebrating? We were celebrating, and this is where Narendra Modi and Macron and Xi Jinping and all these world leaders were celebrating. What were they celebrating? Well, at that time, we had put the first piece in. And guess what the first piece was? It was the cryostat base. So the base was made by India. You can't really see it very much because it's covered up with equipment, but it was put in here. And that was actually the heaviest component that these cranes will ever have to lift. It was 1,250 tons. Brought in here after it was shipped from Hazira and welded all together, brought in here and put on the bottom. Then the next piece was the lower cylinder. So remember I showed you outside in a cocoon, the upper cylinder. The upper cylinder will go here, but right now there's nothing, it's just concrete. The lower cylinder here is metal. So the lower cylinder was put in and it was welded all the way around this circle. It was welded so it could be joined, the lower cylinder to the cryostat base. At the bottom, it's covered up now, but you have the first Chinese-made magnet, which is just barely visible. You can see the edges of it, but the Chinese magnet in here. Then the magnet you saw in the assembly hall will be added next. And then the vacuum vessel sectors will come in and rest on these pieces. This is just a tool, but this tool will be used to stabilize. And at the very end, the central solenoid magnet will come. We have 2 pieces so far from the US. There will be a total of 6 pieces, and they will all be joined together here so that we have then the central magnet, the circular magnets, the D-shaped magnets integrated with the vacuum vessel sector, and everything put together so that we can make 150 million degrees and contain it and make the tokamak, that it will make heat, and the heat will heat the water behind the walls, and the water will go in a commercial plant, not at ITER. At ITER, the heat exchanger will just take off the heat, but in a commercial plant, it will go to actually make steam and drive a turbine to make electricity. So that is the close-up view of this magnificent facility where India and China and Russia and US and Europe and Korea and Japan are all working hand in hand to try to make a machine that will change your future, that will change the future of how we make electricity in a clean, safe, abundant, economically sound way, so that we can leave what I would say is a better energy legacy to all of you and to future generations. So thank you very much for listening. I will conclude the virtual tour and come back to all of you for additional questions and anything else that you would like to share.
So, Nitendra.
To be honest, all of you, the students listening, anybody who is able to come here, I think that the organizers have my email address. Tell me if you're coming. We will give you a tour.
Obviously, we will connect with Dr. Nitendra and we are coming. Let the boundaries be open. So here is the 31-minute video for you from grade 9 who were listening you. And then you take a break. We will display some 5-minute video by grade 11 as well. Over to you, Dilseen ma'am. Please start video.
We thank you, Mr. Lavan, for picking such an interesting topic and telling us about our country's initiative towards the research about the sun.
Although we see the sun every day, this virtual tour has helped me expand my understanding about the different dimensions of our star. I would surely love to know further and attend more such sessions.
I'm really grateful to be a part of such an interesting event. I hope Mr. Lavan would enlighten us more sessions in the future as well.
I'm thankful to Mr. Laban and his team members for igniting our interest in the sun. Would love to attend follow-up sessions.
Great session! We love it!
So excited sitting in grade 9 and there was no access plan because there are many schools who are watching you on YouTube, but these kids said that we want to convey message, but they were on YouTube, so they can't come to MSP. So
Wonderful.
So blessed we are that you are here with through Dr. Nitendra and IYNS team. Dr. Levan, we will just display another tribute from grade 11. They have prepared a very nice type of kind of skit. But sir, if you don't mind, it will take 4-5 minutes. Can you see that? Art integration of...
Absolutely. Please. Yes, thank you.
And then some questions will be posted by Mansi. Over to you, Dilshin ma'am. So, I think there is volume is missing here, Dilshin ma'am. Yeah, you can forward. Yes. Think there is some problem. By the time she's fixing the problem, Himanshi, you can ask questions from audience. Okay.
धियो यो नः प्रचोदयात्
O glorious Sun, giver of energy, remover of sins and ignorance, bless us with consciousness and let us be infused with the glow of knowledge. So says the Rig Veda, a holy book that emerged from the Indian subcontinent and also the foundation of many of the cultures that have emerged from here.
While the sun is no longer considered to be one of the greatest gods here, its importance in our lives is constantly brought up in songs, stories, and in various forms of worship. There are many stories about the sun in all his glory that emerge from here. Here is one which explores the sun as the ultimate truth and asks the question, can we handle it in all its dark glory? And what if we cannot?
Surya was a faithful and a devoted husband, but his wife Sanjana couldn't bear being near him. The problem was that he shone so brightly she couldn't look at him. So one day she asked her maid Chaya to secretly take her place and she slipped away to earth to live anonymously in our world. Chaya enjoyed posing as the queen. She even had a son with Surya, Shani, the planet we know as Saturn today. He was slow moving, rather glum, and not very bright at all. But still, Chaya doted on him and neglected all of Sanjana's children. Finally, Sanjana's children had to report this to their father. Mom isn't just herself anymore, they said. She ignores us and she only plays with Shani. Surya's suspicions were aroused. So when he got home at the end of the day, he would watch her closely. And sure enough, She was only a shadow of her old self. Eventually, he realized, to much of his shock, that this wasn't his wife at all. Who are you? He said. What have you done to my Sanjana? Chaya was terrified. Surya usually glowed with magnanimity, but at times like this, he could be formidable. So she told him the painful truth that his wife had found out that his presence was unbearable and had deserted him. Surya rushed down to earth to seek his beloved love. He found her trotting in a pasture as the form of a mare, so he took the shape of a stallion and ran after her. But Sanjana wasn't eager to return to heaven. You hurt my eyes, she said. You shine too bright. In hopes of persuading Sanjana to take him back, Surya enlisted the help of his father-in-law, Vishwakarman, the great architect whose masterwork is our universe. Vishwakarman tried his best, but Sanjana, she was adamant. She was adamant of staying on earth where she was comfortable. Finally, Vishwakarman came up with the perfect plan. He invited the sun to lie down on his lathe and carefully sawed away much of Lord Surya's light. Then he sent his part down son in law to Sanjana, where she caught the sight of her husband where she could scarcely believe her eyes. She said, You're the most beautiful man I've ever seen, she exclaimed. The dazzling couple returned home and lived happily ever after.
Of course, the Indian subcontinent is one of the many geographical areas which celebrate the sun. Most famously, the sun god Apollo is mentioned in prayers, songs, and plays that come to us from ancient Greece. Listen to these lines from Hymn to Apollo by Callimachus, where the sun, in the form of Apollo, strikes fear in the hearts of enemies.
What force, what sudden impulse thus can make the laurel branches and temples shake? Depart, ye souls profane, hence, hence, O fly, far from this holy place. Apollo is nigh. He knocks with gentle foot the Delian palm, submissive bends, and breathes a sweeter balm. Soft swans high, hovering, catch the auspicious sign, wave their white wings, and pour in their notes divine. Ye bolts fly back, ye brazen doors expand, leap from your hinges, Phoebus is at hand. Ye listening crowds, in awful silence hear Apollo's praises and the songs reveal. Even the raging oceans subside when poets sing the bow, the harp of the Lycodian king. The rich rewards await the grateful choir that still to Phoebus tune the living lyre. From him all honor springs, and high above he fits in power the right hand of Jove. Beyond the day, beyond the night prolong, the sacred theme to charm the god of song. Let all resound his praise. Behold how bright shines Apollo in his robes of golden light. Gold are his quiver, harp, and Olympian bow, and his fair feet in golden sandals glow. All bright gold appears the power divine, and boundless wealth adorns the temple shrine.
From ancient Greek poetry to English sonnets, the sun has been not just a source of power and energy, but a source of knowledge and warmth, of beauty and of love. In his inimitable style, William Shakespeare seeks to find his lover in the sun.
Full many a glorious morning have I seen, flatter the mountain tops with sovereign eye, kissing with golden face the meadows green, gilding pale streams with heavenly alchemy. Anon permit the basest clouds to ride, with ugly rack on his celestial face, and from the furland world his visage hide, sealing unseen to west with his disgrace. Even so my sun one early morn did shine, with all triumphant splendor on my brow. But out alack, he was but 1 hour mine. The regent cloud hath masked from me now. Yet him for this my love no whit disdaineth. Sons of the world may stain when heaven's sun staineth.
Power, energy, light, knowledge, love, warmth, beauty. All ideas we associate with the sun. Zoom back to the beginning. What was before we were? Was it the sun, or was it something before the sun? Carl Sagan famously said, "We are all made of stardust. We are all then made of bits of the sun, and one day there we will belong again." How can we think of all the many differences that make us? Do they not all come down to the singularity from which it all began? We bring to you Singularity from Mary Howe.
Do you sometimes want to wake up to the singularity we once were? So compact, nobody needed a bed, food, or money. Nobody hiding in the school bathroom or home alone, pulling open the drawer where the pills are kept. For every atom belonging to me, this could belongs to you. Remember? To determine if the elephant grieves her calf, or if coral reefs feel pain. Trashed oceans don't speak English or Farsi or French. Would that what we could wake up to what we were when we were ocean? And before that, when sky was earth, and animal was energy, and rock was liquid, and the stars were space, and space was not at all nothing. Before we came to believe humans were so important, before this awful loneliness, can molecules recall it? What once was before anything happened? No I, no we, no us, no one, no was, no verb, no noun, only a tiny, tiny dot brimming with is, 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 all, everything home.
Ma'am, can you stop the video? Thank you. So, I don't know, before we go to Sameer sir, who is our Vice Principal, Gurgaon SNS, and 1 minute to Sonia, I would like to listen from you, sir. How did you like the art integration with science in our school? See, in the morning, Gurgaon students presented a very good bio integration with physics and art, and it was a wonderful session. I'll share all link with you. And now Noida students are integrating, science.
A lot first of all, let me just say that this video, both videos were marvelous, but all of this incorporation by the 11th graders here in the Greek aspects, the Indian stories, the meditations, etc. Yes, I think something very funny. Do you know? Do all of you know about this monument in the UK ancient ruin called Stonehenge, where there is this circle of gigantic stones, right? And a lot of speculation about what was that used for. And we know that there were alignments with the sun, when the sun was in particular configuration at a specific time of the year, at a specific time of day, it would strike the stones just right. So we don't know what that was about, but here's something hilarious, very, very funny. That upper cylinder that you saw wrapped, or the lower cylinder that you saw installed, made by India, it's almost exactly the same size as Stonehenge.
Oh.
It is 10 meters with 30 meters in diameter. So humans, crazy beasts that we are, for thousands of years, have been trying in some way or the other to capture the power of the sun in art, in science, in physics. And so, yes, there is a lot of blending back and forth. I hope that I will be able to get a copy of this video, or maybe you send me the link. I watch it on YouTube or whatever.
Definitely, I'm going to forward, and we are going to forward many questions which children have posted on YouTube, because we are, the students, some of the schools which have joined their school will be off by 2 p.m. So we cannot take many questions, but yeah, Soumya, you can post one question to sir, and we will collate all questions and share with sir by mail so that he can answer and we can float. Yeah, over to you, Soumya.
Okay, ma'am. So we are going to have a question from Angad Singh. How often would the ITER reactor produce electricity using the hydrogen isotopes?
Okay, so ITER itself as a plant will not produce electricity because we're not going to have the electric generator, but it will produce the heat that in a commercial plant could be doing. So how often? I told you about a Q that is supposed to be 10. That Q is in pulses of 400 seconds. And what you need to think about is that when that goes for 500 megawatts for 400 seconds, it's heating all the water. And then at the end of 400 seconds, at the end of the pulse, the temperature goes down. So the power output goes down. But the water, as you know, does not instantly cool down. The water will take some time. So if you have pulses like this in the reactor, you would have the water itself temperature would be more like this. And ITER has a second Q, which is also a design objective, which is a Q of 5 at steady state, meaning that it's the ratio of output to input heating is a little bit less, but it would be to create a steady state. And so that would be continuous production. So how often at ITER, it will really depend on the scientists. How many experiments do they want to do? We have a whole 500 pages of a research plan that will go through, many elements of science. And so it will, the frequency of production, I can't tell you exactly. It will depend on how often the science wants an experiment. But in terms of as we run it as a functional machine, it will either be in pulses that are for 6 minutes and 40 seconds long, and then come down, and then maybe some 10 or 20 or 30 minutes later, they start again, or it will be a steady state where it is continuous production. I want to say one more thing before we come to a close. There is a page on our website that I will be happy to send to you or to any teachers that write to us, where we've put together we released it only about 1 month ago, maybe 3 weeks ago. It's called Infused, which stands for International Fusion Education Program. And it is resourced in many languages for students and teachers who want to learn more. There are posters you can print. There is even, if you want to, you can even print out with a 3D printer your own tokamak and put it together. So this is a little bit difficult, but you can see here we have a lot of the illustrations, and you can use it as a device in the classroom and so forth if you can find a 3D printer. So if the result of this boot camp comes out with more ideas, more movies, more films, things that you would like to bring, you could always send, if you have educational materials that you come up with about fusion, we would be happy to see them and maybe incorporate them into our own page, because we're not making all this. We're just collecting educational material from around the world.
Absolutely, we will do, sir. I've also posted. We are doing a kind of MOU has been signed between IYNS and our school. So throughout year, these nuclear scientists are bringing something or other for us, and the kids are so excited. They know so much. So here we have Samir sir, who is Vice Principal Gurgaon campus. Samir sir, if you don't mind, I'll just take one more minute. Kal sir, we will be sending all the videos, what you said, through Dr. Nitendra to you. And we would like to do some project with you, sir. Our kids are very good. And obviously, when they come to your eater, we are planning through Dr. Nitendra some workshop. We have college also, so college students, and obviously the school, high school students. So they will just come and, want to spend a week like they go to CERN and do workshop with all the physicists. And it's an intense workshop. So thank you very much. We'll take one more minute, Samir, if you don't mind. Here we have a science educator who is just going to convey how we cross campus do things together. Over to Sonia.
Good afternoon, everyone. We all enjoy and assimilate things that we actually understand well, right? And anything that is beyond our understanding, that is something that scares us. And the same holds true for a lot of academic concepts. They scare us. Therefore, in order to brush away all our fears and look at these so-called scary concepts very comfortably, we have been holding fear to fascination sessions where students and teachers from Gurgaon campus, Noida campus, Faridabad campus, the SNS University, and also the Vidya students, they have been coming together and they have been explaining these concepts with the help of an activity. Therefore, we urge you to come forward and share any topic that you want us to take up in this series. Also, we will love if you volunteer to take up these activities. Any teacher, any student, you can get in touch with us via Vinita ma'am via mail. And all of this information is also available on the Carrios website. And we are looking forward to your collaboration and having some fun activities. We are also very thankful to the Indian Youth Nuclear Society and Dr. Nitendra for joining hands with us and putting in so much effort and time to enlighten and motivate the young ones to explore all things science around them. Your collaboration, sir, has fueled our efforts and made events like these possible and a great success. Thank you, everybody.
So this was my deputy science speaking right from here. But there is a person who is an amalgamation of science, geography, psychology. I don't know. He is my friend. He is my colleague. He is my junior. He is my cute little Samir, who is now vice principal of Gurgaon campus. So over to you, Samir, to share your views.
Thank you, Mr. Laban. I think I had to, I mean, in a responsibility being a vice principal, typically what you end up doing is you end up multitasking. And I had a few meetings in between, I was jumping in and out, but the conversation you were doing with children held my attention throughout. So thank you for that, for taking out time to interact with our children. And I think the whole idea of bringing the scientific institutions from around the world of eminence like CERN, ITER, or Indian ones, the counterparts like Indian Nuclear Youth Society or Charles Planetarium, is testimony to our belief that we live in an interconnected world. And that's the key to remember. We can't be chartered accountants, we can't be artists, we can't be scientists, we can't be teachers, we can't be politicians, sociologists, anthropologists, and so on and so forth. What we know for sure is that we have to be a bit of all of these, So I think one of the learning which I was reading about ITER, and I and my friend actually surprisingly discussed about bringing ITER to India about 7 years back. And here we have Vinita ma'am, who's passionately, given us an opportunity to interact with you. While you're pushing the human frontiers of innovation, by establishing technological feasibility of fusion energy, I think what we need to learn from scientific advancements is the skill of resilience. Because every time a scientist fails, he finds that one which way the thing will not work. Now, there are 999 other ways it will work. So you go out in the world and you find 990 ways. You also talk about critical thinking and collaboration. I assume there are more than 35 nations which have collaborated to set up ITER, and there is a collaboration of many more countries. So I think that's the future. So I think thank you so much, and I think beautifully you, as you mentioned, that what has not sun has been talked about in different contexts by science, by biologists, environmentalists, physicists, or for that matter, poets, and prose has been written around it. The idea is that how do we there is enough divergence which has happened over a period of time. How do we converge these ideas to push the boundaries of innovation through institutions like yours in the minds of youngsters, so that we are able to collaborate better, we are able to try to find solutions which COP26 is talking about. We are trying to find the next door problem. It's not necessarily a problem of the world, it is a next door problem. How do I learn what how do I apply what I learned through your conversation today, to build human resilience, to build innovation, and solve my neighboring problems? So thank you, lovely children. Thank you, Vinita ma'am. You've always been an epitome of scientific enthusiasm. I think I can say you are the ITER of Shiv Nadar institutions. And thank you, Mr. Laban. I hope to visit you very, very soon with Vinita ma'am.
This whole thing was possible, Samir, because of Dr. Nitendra. I was trying to reach ITER France, but I could not. So a big thank you to Dr. Nitendra. Yes, uh, we were together in this journey, and we all are like-minded people. Samir, you, Dr. Nitendra, Laban, me, many educators in Shiv Nadar, Dilshin, Rachna ma'am, Ravinder ma'am, etc. So we will be sailing through this world together to bring awareness about the scientific temperament and integrating science with art and other disciplines together. Thank you. Thanks a lot.
Thank you so much.
Thank you, sir. Today, we took part in 4 different sessions and absorbed many interesting facts, which was truly an inspiring experience. Thank you to all the speakers for the wisdom you have so eloquently shared in the sessions today.
So, uh, here is a one poem on our very dear sun. The sunbeam, its shears are dropping hard. To see the glorious sunbeam, its golden light impart. The sunbeams are sunbeam, it smiles on the earth, and through the jewels of the sky, the rainbow springs to earth. So, like the sunbeam, let us strive that our glad light be given to bless and beautify the earth and turn out thoughts to heaven. With this, let's hang out, and link to the website with the resources will be provided in the chat. The session tomorrow begins at 9:30 a.m. and all you need is an open mind and lots of curiosity to join us. With this, we are ending up the session.
Thank you. Bye.
There's one more thing, students. You're supposed to collate, Dilshin ma'am. You're supposed to collate all the questions. We will forward it to Mr. Liban, and obviously we will get answer for all curious mind. We will post it back. Thank you.
Yes, ma'am, for sure.
To all of you, thank you.
Thank you so much, sir.
Thanks a lot.